Very nice to meet you all. So yeah, my name is Ben. I'm going to be telling you all about how to build scalable physics-informed neural networks in this workshop. So let me see if I can just start with an icebreaker. So this is mainly just for me to gauge who I'm talking to today and to try and teach to the right level. So I really invite you to kind of, if you have a device, to scan the QR code or join. Well, the code's been blocked, but that's a bit annoying. Let's get rid of this. Yep, use the code up there, and then just let me know where you come from. I'm gonna maybe move this. Yeah, there you go. Okay, so it makes sense. We have a lot of mathematicians here, perhaps, but that's awesome. We got loads of people from earth science, computer science, physics as well. I have a physics degree, so awesome. I'll give you a few more minutes just to let me know. Okay, so that's good. So it's a mix. I think there's math heavy, but I'm definitely going to try and give you examples across physics and earth science as well, and try not to assume too much math for those people that maybe don't come from a math background. Okay. I have two more questions for you. So how familiar are you with physics-informed neural networks? Chris gave an awesome lecture, Introduction to PINNs, yesterday. So if you haven't have heard of PINNs already, you probably do by now. But I'm interested if anyone uses them for their full-time research or at least applies them. Okay. That's kind of a straight line. I guess I would expect that, yeah. So a real balance. Pretty much everyone's heard of them, but maybe only a few people actually use them or really research them. So yeah, hopefully this is going to be interesting for you. You'll get to see kind of the state-of-the-art physics-informed architectures that I'm using in our research. Okay, last question before we actually start. How familiar are you with numerical methods? So this is not a prerequisite of the course. I'm just interested of your background. Okay, so some researchers. Oh wow, okay, brilliant. So there's actually some really people that really know what they're talking about. Awesome. Okay. So yeah, like I said, the workshop is all about physics-informed neural networks, and everyone's heard of them. This is probably the seminal paper from Ricey in 2019 on physics-informed neural networks. And by now, PINNs have got, well, this paper, maybe 18,000 citations. So by some marks, I heard someone else say at a conference that this is the most cited numerical paper. Don't quote me on that, but I think there's a lot of citations. And actually, since 2019, the number of PINN-related publications, so I did a quick search on Scopus, has been growing kind of exponentially. And I think we were saying yesterday, it's really hard to keep track of just the sheer amount of research that's been done in PINNs. You know, with over 1,000 papers coming out a year, that's too much to read. So yeah, it's clearly a massive research field. But what I do think is, especially in the last couple of years, there's been a lot of pushback on PINNs, and we've started to really mature our understanding of this technique. And I think Chris mentioned this in his previous lecture, this top paper here, which looked at whether critically PINNs can beat the finite element method as a way to solve differential equations. And I mean, long story short, I just cropped this discussion paragraph, and it says, considering the solution time and accuracy, PINNs are not able to beat FEM in our study. So then another paper came out, similar time, looking now at using PINNs to solve inverse problems. So you can also use PINNs to solve inverse problems. I'll talk about that in a bit if you don't know how. And similar conclusions, the fact they use discrete approximation of the equations allows orders of magnitude more efficiency and accuracy. So, I mean, I would take these studies with a pinch of salt. Obviously, there's counter arguments, but I mean, that's the kind of sentiment of some people in this field now. Okay, so what are we going to do in this workshop for the whole of today? So we're going to really focus around this one problem, which I study a lot, but I think it's a really interesting problem for many reasons. And this is trying to model the solution to the damped harmonic oscillator. So this is a 1D ordinary differential equation, very simple equation we know the analytical solution for. And it just models the motion of a mass on a spring with some dampening. And you get this sinusoidal plus an exponential decay. And so what I did is on the top there is I trained a PINN to solve this ordinary differential equation. So yeah, we learned yesterday PINNs are a way to solve differential equations. That's what PINNs are. And yeah, I implemented it in PyTorch, a really baseline model, and boilerplate code as well as I could. So I kind of tweaked the hyperparameters. We talked about these beta hyperparameters. I tweaked them, the number of collocation points, the learning rate, to really try and run it as fast as I could. And I managed to get 82 seconds in Colab on a CPU. So, fairly good. But I mean, who has experience? I think a lot of people here have experience with numerical methods. How fast do you think you could solve this with like a finite difference or even a finite element? Millisecond. Yeah, exactly. So this is just nowhere near competitive. Can anyone raise their hand and like have a guess why? Like fundamentally, why this is slow? What's the big reason? Backpropagation? Yeah. Yeah. Can you expand more? Why is that slow? Yeah. 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 Yeah, great. Yeah. So that's the answer basically. Fundamentally, PINNs require a nonlinear optimization, which typically we do with gradient descent. And that just has a lot of overhead. And I'm training for 15,000 steps if you have a look up there. So that's compared to finite difference, which would just be a straight time stepping method, or FEM, which would just be a matrix solve. That's just not the complexity that's much higher. Okay, so this is what we're going to try and do in today. I'm going to show you two extensions of PINNs, and the goal is we're really going to focus on efficiency. I'm also going to talk about accuracy and convergence rates as well. I think that's very interesting. But the first step we're going to do is we're simply just going to re-implement PINNs in JAX. Hands up who's heard of JAX or has used JAX? Okay, most people by now. Yeah, so JAX turns out for this particular problem to be very powerful. We're going to get an 8 times speed up, hopefully, just again by using boilerplate code. But then the real acceleration gain is going to be implementing a kind of state-of-the-art method that we're developing for PINNs, which is combining them with domain decomposition, and then also training them with linear algebra. So not trying to avoid the need for gradient descent. And that's hopefully where we're going to end up today. And I hope by the end of the session, you will actually be able to code this bottom PINN in JAX and get a millisecond like training time like Chris is suggesting. Does that sound good? Cool, perfect. So yeah, it's also just the second session. Let me go to this. This is the overview. So the first session is going to be very introductory. So we're going to start with just what is a PINN, and I'm mostly going to be lecturing. But then we're going to transition more towards practical. So the second session will be all about JAX. Actually, I'm going to teach you the basics of JAX, and we're going to re-implement the PyTorch PINN in JAX. And then the third session will be all about these kind of state-of-the-art ideas that we're developing. So specifically finite basis physics-informed neural networks, and then training them with linear algebra. Okay. So what I'm going to do now is just zoom out completely. I think it's always important to put things in perspective for any lecture. So I'm going to spend some time just talking about AI for science, scientific machine learning, and then get to PINNs. Just so you can see, well, from my perspective, why PINNs are interesting, and kind of put them in a bit of context as well. So yeah, let's just start really broad. So yeah, I think everyone in this room is here because they know that AI is having a massive impact in science. This is becoming more and more evident every month that goes by. And I'm going to give you like 3 examples of different fields where it's having a massive impact. There's obviously many other examples, and I'm sure many people here are working on impactful work. But this is, I mean, again, Chris covered this yesterday. So in weather forecasting, AI is, having a paradigm change in how we do climate and weather forecasting. Chris was showing GraphCast, but another model which was very early on, very popular, was ForecastNet. So this is a model developed by NVIDIA using FNOs, again, as Chris showed, to do weather forecasting. And this was maybe 3-4 years ago. And I think today they're very competitive. I mean, they have different characteristics, but they are competitive with traditional numerical methods. And yeah, there's articles coming out every day about how AI models can now predict hurricane events, maybe a week in advance, if you believe them. This is a really famous application, probably one of the first famous ones, which was AlphaFold. Again, so this is from DeepMind, and what they were able to do is to train an AI model to take an amino acid sequence. So this is the building block of a protein, and to take or predict from that the 3D structure or the folding of the protein. And so I think the big breakthrough is that what we did before was just to do this in the lab, and it used to take PhD students, lab technicians, months to synthesize these proteins in the lab. So now we can run it on a desktop computer in seconds and get a good prediction. And yeah, I think this is fair to say this has kind of transformed this field of protein design. And there's so many startups and amazing work that's been built on top of this kind of, or these models. This is another really exciting example that came out of Switzerland, EPFL, I think also DeepMind as well. So what they did here is they used AI, or specifically reinforcement learning, to help control nuclear fusion. So this is a real reactor in EPFL, I believe, or yeah, in Lausanne. And what they did is they, so nuclear fusion is the fusing together of elements and collecting the energy that is released, and could be transformative renewable energy source. But the key issue is the stability of the reactor. You're holding a state of matter, a plasma, which is something like akin to what's happening in the sun, and you're trying to contain it. And so what they used here was a reinforcement learning, or a neural network, to control the reactor, to control the inputs and the control settings of the reactor. And they were able to kind of train this agent to kind of not just make the plasma stable, but also to kind of control the shape of the plasma as well. So again, AI is really having a big impact in fusion as well, and giving us new techniques that we didn't have before. Okay, so let's talk about scientific problems and the types of problems that we want to use AI to solve. Like, what are the big challenging problems in science that we actually want to solve? And I think the first starting point are PDEs, partial differential equations. And they are really fundamentally the building blocks of our scientific work today. I think everyone is working or indirectly working with PDEs. They have an uncanny way of describing the universe. So yeah, from the smallest scales to the larger scales. So this is a bit of a quiz. Who can guess what the underlying PDE is? On the top left is quantum mechanics. Who knows what PDE describes quantum mechanics? There's a few. But... Hands up, I need a hand. Yeah. Schrödinger equation, yeah. So black holes, what's the PDEs for that? Yeah, field equations. Weather, you got the answer yesterday, there's loads. Yeah, and then, so this one's really interesting. It turns out biology or natural things can be described with PDEs, and specifically here, the patterns on fish can be described by the evolution of a PDE. Yeah. So yeah, you got it. So yeah, so we care a lot about solving problems related to PDEs. One of the biggest ones is solving PDEs. So I would say the forward simulation task. So here's an example from simulating the exhaust of a rocket. And you can see this simulation running, and it's an incredibly high fidelity simulation. It took 500 million grid cells. I think it was a finite element method, and ran on 8,000 cores for several weeks, at costs of, I think, hundreds of thousands, if not $1 million, generating terabytes of data just to get this kind of 10-second movie. A very important and useful movie, but still very expensive. So yeah, we have amazing techniques for doing simulation: finite element, finite difference, spectral methods, domain decomposition methods, etc. But typically the limiting factor is the computational cost, and that's, you know, one way that AI might be able to help. I would say that there are other grand challenges. A lot of people focus on this simulation challenge, but I would say there's actually other big ones that we could tackle with AI. So I'll go through each of these three areas. One would be up here on the left. So this is a plot of the amount of data that's generated every month at CERN, the particle collider. So you can see, I'd have to remember exactly, but it's terabytes, thousands of terabytes of data every month. So this is just, and it's growing as well. And this is the case for many scientific experiments, many planetary data sets, for example, or missions that we do, or other big science experiments. And so it's just impossible for a human to go through this by hand and look at every data point. It's just completely impossible. So this is where AI could help, maybe, is to pre-process or post-process this data, look for patterns that kind of summarize the data. Another example is the bottom left. This is exoplanet observations. So specifically observations of the flux coming from a star when an exoplanet kind of passes over the face of that star. And what you look for if you're trying to search for exoplanets is like a dip in the flux. So, I mean, who can see a dip in this data? This is basically flux versus time. It's like super difficult. So this is another place where AI could help, is kind of poor signal to noise, like seeing through the noise and picking out needles in a haystack. The issue here actually is completely the opposite to CERN, which is that we don't have enough data. There's maybe tens, if not, or maybe hundreds of possible observations of exoplanets. So if you're thinking about training AI models, that's kind of difficult to do. The final one is, this is the evolution of the COVID virus as it mutated and evolved. And you know, this was something at the time we still really want to understand how the virus mutates. Super important for global health, but it's really complex and depends on, you know, populations, social dynamics, you know, lots of different things. So again, AI could really help us understand these situations where the problems that we care about are becoming more and more complex and harder to kind of understand. Okay, but AI is definitely not the only answer, and this is how we're going to motivate scientific machine learning. There's many challenges, and I think most people are aware of these by now. One of the big ones is just the sheer amount of data that's required to train AI systems. So this is a plot of kind of time versus the size of frontier models. And you know, today's frontier models have billions of parameters, if not tens of billions, maybe trillions. And they're even, you know, we scrape the internet to train ChatGPT and Gemini and these other LLM models today. And this was a paper describing the first iteration of ChatGPT in 2020, and they took 45 terabytes. I guarantee you that's way more data now. So that's kind of difficult for just a standard researcher to grab that data and train a model. That's like difficult to access. I think the other challenge is we still don't really know exactly what the right architecture is to use for deep neural networks. I would argue that that's been a lot of the development and research for the last 20 years. If you think about image recognition, we went from like fully connected networks to CNNs to ResNets to transformers. I mean, what's next? Diffusion models. Yeah, and these architectures can be incredibly sophisticated. Coupled to that is that they're often thought of as black boxes, so it's very hard to interpret what a neural network is thinking, and maybe it's even impossible. Who knows? Yeah. I think the biggest issue, and specifically for scientific machine learning, when we're using AI in science, is this challenge of generalization. And it's the fact that neural networks tend to work well within their training distribution when they see an input close to their training data. But if you query it on an input that's outside of what it's in, it typically performs much worse. And I did this test a long time ago now, but this was ImageNet. I think it was a ResNet trained on ImageNet. So natural images for classification. And it works brilliantly on an image in distribution, can get the breed of the dog, but on a space dog, it just doesn't work. And it's to be expected. But I mean, you see another thing here, which is that it's overconfident. It thinks it's a lab coat with 40% accuracy. So I think we also see this in LLMs today, is this whether they can actually reason, or maybe a better question is like, do they reason in the same way as humans? And they have very different characteristics. So this was a meme at some point, asking, I think this was stable diffusion, so like a state-of-the-art image generation, to generate a street with absolutely no lampposts. And it just really struggles with that negation in the logic and just sees the word lamppost and attends to that, and then just generates loads of lampposts. So again, these are real issues. And I think when you talk to kind of scientists that are skeptical of AI, this is what they get hung up on, is that it really goes against our scientific method, which is all about like coming up with a really interpretable PDE or model, like verifying that model with experiment and then updating the model in a very transparent and iterative way. And that's very different to these kind of black box, one-shot neural networks. So here's just to hit the point home once more, that these things really matter when we apply deep learning to scientific problems. So this was the first project that I did in my PhD, which was my first time using deep learning. And I was trying to do seismic simulation. So solving a PDE, in this case, the wave equation. And the input to this model was basically the velocity model of the Earth. So this, you can see on the left here, this is a slice of the Earth, a very simplified view of a fault with geological layering. And you can imagine that there's a seismic source or maybe an earthquake that's starting here. And over time, it propagates to the surface, and we've got a bunch of receivers on the surface measuring the kind of seismic response. And so what you record on the surface are these things called shock gathers. It just basically is the x-axis here is the offset of the receiver, and the y-axis is the time. And you see these arrivals of seismic energy come in, and it's really interesting to understand that in more detail. But yeah, I generated lots of training data with finite difference simulation, trained a very standard convolutional encoder decoder. And yeah, you see the same thing. I trained it on these layered single faulted models with just horizontal layers, and within distribution it works really well. But as soon as I test it on these like dipping layers with curves or other angles, or maybe multiple faults, the predictions just go way off. And so yeah, this is the issue of generalization of these high dimensional function approximators. Okay. So that kind of motivates scientific machine learning, and what I'm going to try and do is explain from my perspective what SciML is. People have different opinions, but yeah. Yeah. Yeah, so the generalization task here is I trained it on models that were just horizontally layered. So these velocity models that just have these horizontal layers. And I want to test if it works on models that don't have horizontal layers, but like angled layers instead. So these ones on the bottom. Yeah. And it doesn't work, basically. The performance significantly degrades. Yeah.
So during training, there was no data augmentation or something like that.
Right. So there are many tricks that you can do to improve generalization. But I would still argue, even with those tricks, there'll be some input that's far enough away still that won't work. Yeah. So a good example might be, even if you did that augmentation, if I increase the frequency of this seismic source to like 10 times or 100 times, I guarantee you that would be that's for traditional methods, that's really hard to simulate, very expensive. And I'd be incredibly surprised if this model did that without extra things in the model. Yeah. Yeah, so scientific machine learning. So it's a relatively new field. So I think we're still as a community figuring out exactly what it is. But here's my perspective. I would define it very generally and very simply that what we did before SciML was what I just showed you, which is this very much treat AI as a black box hammer, where you have some scientific problem or workflow. So mine, for example, was to simulate seismic waves. You have some inputs, which would be, in my case, that velocity model and where the earthquake starts. And then you have some predictions like the seismic response or something else. But this could be something completely different. It could be the amino acids of a protein and then predicting the 3D structure as the output. And you just generate loads of examples of those inputs and outputs, a huge amount of data usually. And then you train some model. You just treat it as a black box. Or you might design it if you think you know something about the task. And then you just hope it works. Yeah, and this suffers from all those issues that I was just describing. So the kind of lack of interpretability, it requires loads of training data normally. And yeah, it struggles to generalize. And these are just kind of well-known properties of deep neural networks. So SciML is different. What we try and do is just open the black box at the highest level. And instead of just treating it as a black box, we really try and incorporate scientific principles into that machine learning workflow. So there are so many ways to do that, but that's how I would define a scientific machine learning algorithm, is to really think about the scientific principles and the kind of physics constraints and things like this, and design a principled machine learning workflow on top of that. Yeah, so the kind of thesis of the field is that if we do this, then we'll design more powerful, more robust, more interpretable algorithms. And I certainly see that in kind of the research that's happening in SciML today. Okay, so here's a word cloud. I generated this a few years ago, but so there's way more techniques now. But the point of this slide is to say scientific machine learning has a plethora of techniques. There is not just a single technique. PINNs, we're going to focus on PINNs today, but they're just one of maybe hundreds. And I could give lectures on all of these, and it would take a whole month's course to do it. But yeah, you might have heard of some of these previously in this week, or maybe coming up as well. So I think we talked about neural operators yesterday, differentiable simulation, neural ODEs, hybrid workflows. These are all methods that are really interesting. And yeah, I would say that SciML is definitely a rapidly growing field. It seemed to have kicked off, again, this is another keyword search that I did on Scopus for key terms in the field of SciML. And it does seem like it kicked off around 2018, 2019, when the PINNs paper, when that seminal RISE paper was published. And since then, today there are so many SciML-based conferences. I mean, we're at one today, so but all the big machine learning conferences have SciML workshops. I'm actually really excited about this one coming up. It's the differentiable systems. That's going to be at Europe's just in a month or two. But yeah, there's a lot going on. And then I think my final kind of high-level observation is that the real trick to doing SciML well is to be as interdisciplinary as you can. And by definition, if we're talking about fusing machine learning with domain knowledge, you already have to know something about ML and your domain that you're working in. But I think you also need to have these other things like, PDs are fundamental to science, having some applied math experience. High performance computing to train large scale models is important. And I think no one person has all of this. And I think the real key is to really collaborate. And I really love doing this. This is why I do research in SciML, is to work with really incredible people that have different perspectives and problems that I can help with. So I really encourage you, if you want to move in SciML, is to really work around this circle as much as you can. Okay, so I'm going to just ask this question, and then we'll take a little break before we talk about PINNs. So this is my last kind of high-level section. So yeah, the natural question is, if you're going to start incorporating scientific principles into machine learning, well, how do you do it? And I think I just hinted that there's actually hundreds of ways of scientific machine learning methods that we could study. I like to break them down into kind of 3 categories. There are other ways to break this down, but it's a good starting point. And if we're just talking about deep learning, which is 99% of SciML and AI research today, then we're talking about deep neural networks. And then I would say there are kind of three ways. And the first is through the loss function. So you can add physics constraints like conservation of energy, symmetries, etc., etc. And that is like a kind of soft constraint of the network. Physics-informed neural networks are exactly that. And I think Chris said that he didn't like the name. I agree. I think it should be called physics-informed loss functions. I think that's a much better idea. But there's other ways. So the architecture, you can hard constrain the architecture to give you physical outputs, again, so that it has some translational invariance. CNNs are kind of a good example of this. The final category is what I'm working on quite a lot these days now is what I would call hybrid approaches. And this is where instead of kind of throwing away your existing scientific workflow, you keep it and you really think about incorporating machine learning into a key component of that workflow. So for example, if you have like a finite difference or finite element solver, we know that that's an amazing algorithm, but there's some bottlenecks in the algorithm that are too expensive. And so what we're going to do is we're going to go in and replace that with an ML component and think really carefully about what exact component should we replace and how are we going to train it. So examples of this are neural differential equations, differentiable physics. There's a lot of really exciting stuff going on in this bit as well. So again, nearly 3 years ago now, I tried to lay out some of these category subfields of SciML onto this spectrum. I think this is another way to kind of slice and dice these SciML methods. Other people have shown this many times, where on the left of the spectrum, you kind of have your naive machine learning techniques. And then on the right of the spectrum, you have your traditional workflows. So maybe on the left, it's like fully learned. There's no physics, if you like. And it's completely reliant on data. And on the right, it's completely the opposite. So there's no learning. Everything is hard-coded, all your physics assumptions. And yeah, no data required. And this is obviously very subjective, but it's kind of fun to kind of place these methods in these different along this spectrum. And so you might say that the loss functions, they're kind of just soft constraints. So then maybe more to the left, you're really relying on an ML model. Whereas these hybrid models where you're putting something inside an FEM, that's maybe more to the right. And you have much more control on the physics. So if you're interested more, you can have a read of my thesis. This is I really tried to survey SciML methods at the time and kind of place them in these boxes. So yeah, we're going to talk about for this whole day, we're just going to focus on this one box, which is the loss function, and specifically PINNs. We're going to think about their limitations and how to really accelerate them. And I think what I'm going to do there is just stop. We'll take a 10-15 minute break, and then we'll get really into the basics of PINNs. Okay, everyone, let's get started. So we're now going to talk about physics-informed neural networks. And this part is just going to be a basic introduction to PINNs. I appreciate you had an introduction yesterday. I think it's good to tell you from a different perspective, perhaps, and to just help you remember what was done yesterday. So what is a physics-informed neural network? I wrote a blog post on this a long time ago, and it's been picked up. I don't know if you see these things on LinkedIn, but for some reason, viral influencers love to someone's cropped my GIFs and turned them into this thing here, and then it's been shared many times. I don't know if you've seen this. But yeah, this problem, this harmonic oscillator problem is what we're going to be focusing on, and you'll probably be sick of it by the end of today. So yeah, so as I said, a PINN is simply a way to solve a differential equation. That's really all it is. Of course, there's many interesting things you can do with that, but that's the basic statement. So I'm going to show you this particular ordinary differential equation and how a PINN would solve this equation. But it's a general purpose method. It can solve many different types of equations. So we're going to talk about the harmonic oscillator. So this mass on a spring with some dampening. And we know what the ODE is. It contains an acceleration term, mass times acceleration, plus a velocity term, where mu is the coefficient of friction, and then k is the spring constant, which kind of determines the frequency of the solution. So we're going to set it up with these initial conditions so that we can define a kind of particular solution. So specifically, the mass starts with a displacement of 1 and a velocity of 0. And you can see the solution here. As I said before, we know for this case, the exact solution. It's a sine wave modulated by an exponential decay. Okay. So how does a PINN work? It's really, really simple. And this is the big key idea of a PINN, is that you use a neural network, typically a fully connected network. You can use other ones too, to directly approximate the solution to the PDE. So the network is a functional approximation of the solution. So the neural network, every neural network, is just a mathematical function with a lot of parameters. And so we're going to say that mathematical function, neural network, as a function of its inputs, is going to approximate the solution U of the equation. So in this case, our equation is a 1D equation. So we're outputting a scalar, we're inputting a scalar. The input is the time, the output is the displacement, U. So in this case, the network should have one input, which is time, and one output, which is the displacement. Who's with me? Good. Okay. So that's the most important idea. That's the thing you need to get. Okay, so the next question, and this is where it gets interesting, is how do you train PINNs? And if you come from a machine learning background, you're thinking, what's the training data? And kind of a supervised loss function. And what's interesting with PINNs is they're trained in an unsupervised way. So we don't need examples of the solution. What we need is two things in the loss function. The first is to make sure that the solution the network learns obeys the boundary conditions. This is really important to make sure it learns the correct particular solution that you want to model. And so this is a supervised loss, if you like, which is, we just say that the network prediction. So here we're saying that U hat, so instead of NN, we're just going to call it U hat from now on. So then the output of the network here at time equals 0, with the parameters of the network labeled by theta here, is going to be 1. We're going to have a mean squared error to match it to 1. Now it gets a bit more interesting when you think about the velocity boundary condition, because this is a condition on the gradient of the solution. So we actually use this as a direct constraint in the loss as well. We say that the gradient of the network with respect to its input time at time equals 0 should also equal 0. And we do a mean squared error on that. So we would call this the boundary loss. And then the second loss term is the physics loss, also known as the PDE residual. And this is where we say the whole solution, over the entire modeling domain should obey the underlying differential equation. That's, by definition, we want to solve the equation, so the solution should solve the equation over the whole domain. And so we have a term here which evaluates the residual of the equation. So it evaluates the left-hand side of that equation. So it takes the neural network's prediction at many time points, evaluates the first order, second order gradients, collects them into that left-hand side, and then forces it to be 0 with a mean squared or a squared error, basically. So we do this over many points in the domain. So you see the summation over I. So we call these co-location points. This is what Chris was talking about yesterday. So yeah, boundary loss obeys boundary conditions. Physics loss obeys the underlying differential equation. Everyone with me? Good. So this is what happens when we train a PINN on this particular problem and initial condition setup. So the blue line is the prediction of the neural network as it trains. The gray line is the exact solution. And the orange dot on the top left is just showing that initial condition or the boundary condition. So yeah, like we said, we're saying that it should start at 1 and with a velocity of 0. And then the green points are the co-location points. So those are the points in the summation of the physics loss where we're asserting that the PDE should be obeyed. And yeah, you see that this network trains, just like I showed at the very start, within 10,000 steps or something like this. And yeah, I mean, it's a really interesting model. The first time it came out, it was a really cool technique to study. I don't think I'd seen anything like it before. But actually, it is a bit like, or very like these standard collocation methods if you look at it from a numerical point of view. Yeah. Any questions on this? Or does that make sense? Yeah.
And you see that it first it's the high amplitude part to
Yeah.
the left, and then it
Yeah.
struggles to with the rest.
Yeah. Yeah. So to reiterate that, so it really quickly fits the boundary condition or the initial condition, and then takes a long time to get the high frequencies. Can anyone actually postulate why? Anyone with experience with pins? I don't know the right answer, if that helps, but I have some guesses. Yeah.
Signal is less.
The error signal. Yeah. 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 Sure. So. Yeah. 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 Could be that. Yeah.
I'm thinking that damping and all those other terms don't matter at the boundary, so
yeah,
it has less to do at the starting point.
Yep, that's another reason. Yeah. So go on, Hankus.
So it's loss is very into an altitude normal something. So
yeah,
you're gonna get the spectral bias going on.
Spectral bias. Yeah, definitely. Yeah. So I think it's complicated. There's lots of reasons. I would say a big reason, we talked about this yesterday about these hyperparameters. So I haven't mentioned yet these lambda values, lambda 1 and lambda 2. What would happen if I chose lambda 1 to be very large? What do you think would happen? If it was like way bigger than lambda, the other ones?
It would fit the boundary condition much faster than the rest of the.
Yeah. It would, or maybe it wouldn't even give a good solution. It would just snap to the boundary and that's it. What would happen if I went the other way and just weighted it down to 0? The two boundary terms.
They wouldn't know where to start from.
It wouldn't know where to start from. So what would it do? It would be a non-unique solution. Yeah, it would be any solution. So there's infinite amount of solutions. What actually happens, I've done this before, is it just learns 0. Because 0 is like a trivial solution to this equation. So
if you check how the residual looks like, because the residual is actually quite small.
Yeah.
Even if it does not learn what happens on the right.
Yeah, that's a great comment. So this is a good way to diagnose pins, is to plot the residual. So basically this evaluation of the left-hand side of the equation without doing the summation and the squared. And you can see like how strong that error signal is, like you were saying. And yeah, Alexander is saying that might be very small. Yeah.
Yes, if the error signal is small, the gradient won't flow when
you yeah. So this like for every pin, I would say there's this like struggle between the terms. Like the boundary condition might not want to have the same solution as the PD, the physics loss. And that competition makes the loss function like really non-convex. And this is why they're hard to optimize often. So yeah, there are ways to get rid of the boundary loss. You can use hard constraints. I'm not going to talk about this, but I have a whole lecture series on extensions of pins that I can send around afterwards. Okay, so it's just some definitions. So collocation points are these TI points. I totally agree with what Chris was saying, where you should pick those very carefully instead of randomly. Quadrature methods are a great idea, or quasi-random at least. And then the scalars are very important, and you really have to. I also agree with Chris. Probably I do it by hand, but there are methods where you can kind of learn these at the same time and adapt them and use kind of theory like neural tangent kernel theory, for example, to aid them and things like this. So, okay, so here's the training loop, because this workshop is about practically implementing pins. So we need to talk about the training algorithm. So it's fairly simple. So you start by just sampling your input points. So your boundary point, in this case, we just have one. In higher dimensions, you'll have a set of boundary points. And then your collocation points. And then you compute your outputs to get your first boundary loss. Then you have to do something a bit weird, which is compute the derivative of the output with respect to the input. Then you have to collect all those derivatives appropriately to get all the loss functions and then compute the loss. And then you have to do another gradient, which is the gradient of the loss with respect to the parameters of the network to do gradient descent to train the network. And so this is the non-trivial thing about PINNs, is you're doing some more complicated gradient manipulation than you would do with a standard neural network. So this is my question. Can anyone tell me how you would actually get these gradients, like du by dt and dl by d theta?
Maybe you can implement a weak form.
Weak form, yeah. So the weak form can lower the order. Yeah. So definitely you could do that. Yeah. So that's sidestepping. But how would you, if you had to, how would you do it?
Yeah, so PyTorch.
JAX or PyTorch? So yes, but why? What do they do? Yeah. Also diff. Yeah. So does auto diff work when you? I just said you have to get one gradient and then do another gradient through that.
Yeah, I mean,
Okay.
you can show.
So it does work, but it's magic basically from our point of view. But I would really encourage you, I don't have the time to talk about it, but to understand under the hood how PyTorch is doing this magic, because it's really clever. And it's building computational graphs, creating new graphs to compute gradients, and then creating new graphs to compute gradients of gradients. And you should also understand the complexity of that. And it gets quite expensive when you want higher order derivatives. So yeah, the easy answer is we just used AutoGrad, but the hard answer is learning AutoDiff. Yeah.
Understanding JAX works slightly better compared to PyTorch.
Well, for this benchmark that we're going to do, I'm claiming you can get an 8 times speed up. So I don't know if that's a general, it's probably not a general statement, but yeah, for sure in this problem, it works. Yeah. I've got some ideas why, and in the second session when I talk about JAX, maybe I'll tell you. Yeah.
Decomposition from PyTorch.
No. So this is would be a great thing for you to do and to tell me if it's more performant. Yeah. Okay, so this is the original experiment. Chris covered this, I think, in his lecture, so I won't go into it in detail, but this is just to show you PINNs can solve many different equations. This is a 2D equation now, the Burger's equation, nonlinear. But the same idea is, it's exactly the same setup where you assert your boundary conditions in the boundary loss, and then you assert your PDE residual in the physics loss over many co-location points. In this case, we have the Burger's equation. And now the boundary loss is not just a single point, it's the boundary condition here is across 3 of the edges of the computational domain. So yeah, so you need these summations in your boundary terms as well. But long story short, they solved this well in the original paper. And what was quite interesting is they actually managed to model the shock. So this is an interesting problem because you get a shock that forms in the solution. So what you really you're modeling the flow through a pipe, for example, like a 1D pipe section. And you start with a flow where some fluid is going this way and some is going this way, with a sinusoidal difference pattern, but then a shock forms quite quickly. And that's just really numerically quite hard to simulate traditionally. PINNs are not actually, still struggle with shocks. That we actually have a review paper that came out recently. I can point you towards that on that topic. Yeah. Yeah.
It's interesting for me to know, what do you think, for example, if we compute using automatic differentiation of derivatives?
Yeah.
So in the end, we get pointwise values.
Yeah.
So
Yeah.
we set it coefficient.
Yeah.
And of course, some people in the PINN community, they try to embed some sort of defined difference discretization
Yeah.
into the loss,
Yeah.
which somehow captures the
Yep.
structure of the differential operator.
Yeah. Yeah.
This is on forever.
Yeah.
Like this type of derivatives which are evaluated point-wise. Do you think it's a disadvantage of PINN?
Yeah, so there's been papers, extensions of PINNs where they claim, or they say that AutoGrad is expensive, especially for higher order derivatives, because you have to build more and more computational graphs. So one way to get around that is to use finite differences, or more cleverly you use stencils, which are like designed specifically for that PDE, which is what you're talking about. So that works for sure. You can get speed ups. They're not amazing. They're like 4 to 10 times. They're not like multiple orders of magnitude. And always the issue is like the width, the discretization width. It's another hyperparameter. But then other people say that noise of not exact gradients can help with the optimization. It's a bit like stochastic gradient descent, that you're not going straight to the minima. So again, it's kind of a dark art. Yeah, it's a bit of a dark art, and whether it works on one problem, maybe it doesn't work on another. So yeah, it's hard. So if you're interested, these are the specific parameters they used in the paper. So they used 10,000 collocation points, which were pseudo-random, 100 boundary points in each direction, a fairly deep neural network, 3,000 parameters, so nothing massive, but deep enough, and tanh activations and a second order optimizer. So that definitely can change the convergence for sure. Okay, so I just gave you the basic definition, but as I hinted at, this is now a field of maybe 6 years, 7 years. Actually, some of the original contributions to PINNs came out in the 90s. There's papers by Lagaris and other people. So you could argue that PINNs has been around for a very long time, but the explosion of interest has been after that 2019 paper. So okay, so I'm gonna talk about the key tasks that you can do with PINNs and go through it fairly quickly because I want to get on to coding, so a code along. So yeah, what tasks do we have to solve? Well, I just showed you how to solve forward problems, so simulation problems with PINNs. But it turns out you can do 2 other big scientific problems with PINNs. And one is inverse problems, and the other one is model discovery. So I kind of illustrated these different types of problems with this example of seismic simulation, but you could replace that with any kind of forward and inverse problem, like fluid simulation or protein design or something else. So yeah, the forward simulation is like given your initial conditions. So in this case, the velocity model and the earthquake location simulate the seismic response. But the inverse problem is to go backwards. It's like given some observation of the system. So you might record the response of the seismic waves at the surface. You actually want to understand what the structure of the Earth is. And then the model discovery is to say, well, given observations of everything, like the outputs of the system, but also the inputs as well, can we actually figure out what the underlying PDE is? Can we discover the equation? So that I would call that model discovery or equation discovery. So PINNs can do all 3, and that's another reason why they're so popular and so researched is you can do this as well. So I'm going to briefly show you how to use PINNs for inverse and equation discovery. So just before that, one more example of using PINNs for the forward problem. So I've done, this is my next project in my PhD, which was to use PINNs to solve the wave equation instead of a black box network. And yeah, same setup as a standard PINN. So in this case, it's a 3D simulation, 2 spatial dimensions plus time. So we've got the X, Y, and T inputs to the network now. A single scalar output is the acoustic wave equation we're modeling. So it's just pressure. Kind of same setup. We've got boundary data. In this case, we actually used a finite difference, the first time step of a finite difference solver to give us our boundary or initial wave field. And then we had the standard kind of physics loss wave equation in the physics loss. So yeah, this is just the output after training the PINN. So the PINN solution is on the third row in the middle. What I also compared it to, so you can see the PINN can learn the wave equation, which is really cool. We've never seen that at the time. It also models the kind of reflections when the wave hits different interfaces in the velocity model. And it also gets the kind of squashing and the expansion of the wave field as it goes through different velocity regions. So it's learning like complex physics, as you would expect if you solve this equation. The naive network is interesting. That's where we got rid of the physics loss and we just trained it with the boundary loss. Like I did that thought experiment earlier. It snaps to the boundary condition. Interestingly, it gets the idea of the wave field like moving outwards, but doesn't get that complicated physics because it's not constraining in the rest of the domain. So that's the kind of comparison. But this was a more complicated solution. You can see it's a bit high frequency than the Burger's equation or something else. And so this took a bigger network. It was like 10 layers, 1,000 hidden units. Yeah, quite a few points to train it. Okay, so what's interesting is you can use the same idea for the wave equation, but to solve the inverse problem. So this is to where we don't know what that velocity model is that the wave is propagating through. So this is an example here where imagine you have a vibrating plate, and that plate has a crack in the middle of it somewhere. So you're vibrating it, and the goal is to like look at the scattering of the vibrations and use that to invert for the crack, where the location of the crack is. So this is something we do in non-destructive testing. So the type of data that you would actually record would be the amplitude of the vibration or the displacement of the plate as a function of time. So you would get this kind of data up here where you're seeing like a wave going through the plate. But somewhere in there is a crack, and we want to find out where the location of the crack is. And you can kind of see, if you have a trained eye, you probably would think it's here because you see some reflections. What we really want is this underlying velocity model, because we would see the crack as like a perturbation in that velocity. So what you do is you say, okay, we're going to train a PINN to, again, learn the solution of the wave equation. So to model the displacement as a function of time. So exactly this data. And in this case, we have lots of data. So we're assuming that we've got access to all this observational data here that might be maybe noisy. And what we say is the output of the PINN should match that data. So now what we have is, instead of a boundary loss, we have a data loss. So this is the cool thing with PINNs, you can add data constraints. So the PINN just needs to learn to match the data. And the other cool thing is that we have that physics loss as well on top, as we do with a standard PINN. So we, again, sample co-location points, and we say that everywhere the solution should obey the wave equation, because that's what's happening here. Now, the key difference when you use a PINN for an inverse problem is that, and this is the kind of trick and the really neat idea, is you say, actually, we don't know something about this equation. And what we don't know is the underlying velocity model in this case. So this is the 1 over c squared term in the wave equation. And this is not just a single value, this is a spatial field, because the velocity model is a function of x and y. So what this paper did, a really interesting paper, they, at the same time as using the standard network to model the solution, u, they added another network to model the velocity model. In the same way that a PINN works, it took the kind of spatial inputs, the x and y, and then instead of giving you the displacement, it gave you c, the value in the wave equation. Everyone with me so far?
So this is a static field, right?
Static field, yeah. So it's just a static velocity model, yeah.
Just have what's all the what's.
Right. So how you train it? That's the question. Yeah.
For the immersion, I need to construct a neural network for each field variable. Another.
Yeah. Yeah,
Okay.
maybe. Or you can actually have multiple outputs from the same network to model multiple variables at the same time. It's possible.
It's another.
Yeah.
And are you training both networks simultaneously, or are you training the data loss first and then?
Okay, so let's talk about training. So the neat thing is that you train this just like you train a PINN. So you optimize this loss function, the data loss and the physics loss added together, and just use gradient descent. And what that does is whilst you optimize the parameters of the PINN, the theta parameters, you also jointly update the parameters phi of the velocity network. So the optimizer is optimizing both at once. So as the PINN trains, it's fitting to the data, fitting to the PDE, and under the hood learning like a velocity model, which is pretty cool. It's cool. It's kind of cool to see that train. I've got an example of that coming up when I'll do some coding. Does that make sense? Yeah.
I have a question also regarding data, because on the picture you can see some high frequencies.
Yeah.
And I wonder, let's say, if you sample your data,
yeah,
which covers, let's say, only maybe the coarse
yeah,
scale structure of your equation.
Yeah.
Embedding this physics informed loss, does it help you to resolve the high frequencies in fact? Or you
Yeah.
need to sample densely?
Yeah. So this data loss, I think really helps the stability of the PINN. So the PINN will train easier if it's a supervised loss is usually the easiest loss. Physics losses are harder to optimize often. And this is very dense data. So the PINN does a great job of modeling even the highest frequencies in this data. So actually the top right here is the PINN solution after training. So this is the output of the PINN, the displacement network. You can see it's modeling the solution really nicely.
Do you have a picture how the data is scattered, or it's really scattered along the whole domain?
It's the whole domain. I think it's this whole picture on the left, every pixel.
Uniform.
It's data.
It's data, yeah, it's real data. Yeah. Yeah, so it may be easy, but for the point of showing you how it works, I think it's really nice.
Because in this work of Numerical, in the scroll,
Yeah.
he was considering the stocks problem, but
Yeah,
for data was only on the subdata.
yeah,
and
of
there was
course.
no bound.
Yeah, so inverse problems in general can be very hard. They usually are when you don't have as much observational data. They become very ill-posed. So you still have the same issues when you train pins as when you do any other inverse problem. But you can use tricks. You can have priors on your velocity and stuff like this. So. Okay. Yeah.
Like if you actually have full data, I'm actually wondering if this is actually a sensible idea to use just a fully connected neural network because you are in a 2D domain, right?
Yeah.
It seems bizarre to me that like you are not
Yeah.
you are given this
Yeah.
like spatial independence like
Yeah.
really on a plate and you are not deploying that.
Yeah, so we started with fully connected because it's the easiest for a spatial field. Yeah. Has anyone studied neural fields? Do you know this is like a whole thing in computer vision? Same idea where you parameterize the field with a fully connected network. But there's been other models. That's a whole, again, maybe 100 papers and pins are about different architectures. So yeah, for sure. Okay, so this is the output of the velocity model of the velocity network after it's been trained. So obviously it's a fully connected network. We query it over the whole domain and plot the predicted velocity. And yeah, it puts a perturbation where the crack is most likely located. So, okay, the final thing I want to cover is model discovery. So this is a very busy slide and it's quite complicated. So I'm just going to tell you at a high level how it works. But the key thing here is that we don't actually know the underlying equation. We want to discover the PDE rather than just like maybe a field or a parameter in the PDE. So what we're going to do is we're going to train a pin to like discover that equation. So the first thing you do up here is you have to make some assumption of what the form of the equation is. And you say that up here, that the derivative of the solution with respect to time minus this thing here, which I'll explain, is 0. So that's the underlying general form of the equation. But what you say is that this thing here is actually a bunch of operators on the solution. So this is what we would call a dictionary of operators. So if you can see it, I don't know if you can see, but this dictionary might be like, you might evaluate the solution, the derivative of the solution with respect to time, the spatial derivative, the second derivative, and you collect them all up into one big vector, basically, of all the possible terms that could be in your underlying PDE. And then you write down your PDE is that big vector times by some matrix of coefficients. And that matrix determines like which terms of those entire dictionary, which of those terms actually are part of your equation. So this is this big matrix here. And the key point is that that matrix is very sparse. There's only maybe a few terms in your dictionary that actually show up in your equation. And so now the kind of what you've done is turned equation discovery into an inverse problem, basically, where the problem now is just to learn those coefficients of this big lambda matrix. I hope that makes sense. So I'm going quite quickly through this.
It's compared to Cindy.
It's very much like Cindy in that Cindy does this. It has a dictionary and a sparse matrix, but the data and the underlying model is a bit different. So what you do is this is your pin, standard pin. It takes in, say it's a 3+1D problem, so time varying 3D problem. Takes in those coordinates, and then you get the solution, proposed solution of the underlying equation. Then you use autodiff to get this library of operators. So you collect all these different derivatives and whatever you want in your dictionary. So you actually evaluate them, that whole vector. You times it by your proposed coefficients, and you use that to evaluate your PDE loss. So that's how you have your physics loss in your loss function. And then you add this data loss. That's the key thing to actually discover the equation, is the observations of the solution, just like I showed you before in that inverse problem. And then you hope that as the pin trains, it learns the coefficients of the matrix, thereby discovering the equation, but also fits your data well. And you can imagine we're talking about ill-posedness. This is even more ill-posed, depending on your dictionary and things like this. So this paper was, came out, published, I think, in Nature Communications. Really interesting paper. They actually do a lot of tricks. One of them is that they alternate between updating the physics loss and the matrix of coefficients. They do interleaving. Anyway, so this is an example of data from the Burgers equation, but we're now assuming we don't know what that underlying equation is. But what we do have is many observations of solutions from that equation. This is the top row. And we're training the PINN to fit that data, but then as you see on this middle graph here, this is the coefficients, various coefficient values of the matrix as a function of training step. You see that it starts to set some of those coefficients to 0 and keep others. And that's it, kind of learning the underlying equation itself. And the final output is like a PINN that fits the data really well. And the final expression, which kind of closely matches the Burgers equation in this case. So yeah, really interesting study. It's worth a read. Yeah. Yeah. Yeah, so you do assume you know the form of the PDE, but it's written in this general form. So you say du by dt is some vector of operators times by a coefficient matrix. So that encapsulates a whole class of PDEs with different coefficients, and the goal is just to learn the coefficients. So you can evaluate it. You just, as the PINN trains, it's like training on different PDEs as it optimizes the coefficients in the matrix. That's what's happening. Yeah. Okay, so I'm going to continue, and we're going to move to a code along. So this is basically where I'm going to be coding a PINN in front of you in Colab. And I encourage you, if you'd like to follow me along, so you can use this to go to the GitHub, which contains all the code for the workshop. And you can write the code with me if you want, or you can just watch. Yeah, there's no need to write if you don't want to. So just give me a minute. I'll just set myself up. Okay. So has everyone got the chance to look at the GitHub who's going to follow along? So you can, this is the link. Hopefully it should work for you. And what you have here is the structure here. So this contains links to the slides that I'm showing, but also all the notebooks that we're going to be using. So yeah, feel free to browse that whenever you want. So we're just going to click this Open in Colab training a PINN in PyTorch. And hopefully it will just create a Colab session. Yeah, so hopefully you can do that. And we're just going to run this anyway. Okay, so we start just by importing PyTorch. So this is what we're going to use. And our problem is, again, the harmonic oscillator. This is the underlying equation. This, if you're interested, is the exact solution that I was referring to. And yeah, we're going to use a PINN. We're going to use a PINN to solve this. So I'm just going to start by defining a few key functions. So this just evaluates the exact solution. And this is just a boilerplate fully connected network in PyTorch. So I'm not going to explain this, but if you're not sure about how this works, check this out afterwards. It's just a bunch of fully connected layers, very standard setup with a tanh activation function here. Okay, so we're going to train the PINN. We're going to use exactly the loss function that I described in the lecture. And we're going to be using Torch AutoGrad to use AutoDiff to get the gradients that we need in that loss function. Okay, so what I've got here is yeah, a minimal code to train the PINN, so as minimal as possible. And there's just a few key things that I need to write in. So I've kind of got the structure already, and I'm going to show you the key parts. So the first thing we need to do is define the boundary point. So this is that single point in the boundary loss at t equals 0 to evaluate the PINN at. So we're just going to do a torch.tensor. And we're going to say that it's 0. So we want, sorry, 0. We want to evaluate the PINN at 0. time equals 0. Yeah, sorry if it's not big enough. Is this big? Is this better? Any bigger? Can you see at the back? Bigger, okay. Okay, I hope this still works for me, but it should be okay. Okay. So I need to do one other thing, or two other things. I need to reshape this tensor to give it a batch dimension and then an input dimension. This is just how PyTorch works with its neural networks. This is the expected shape of linear layers. There's one other thing I have to do, which is add a flag. This requires grad flag. So and I need to set that to true. So anyone know why I have to do that in PyTorch?
If it doesn't want to compute the areas, if it doesn't have to.
Yeah, so if you didn't hear that, PyTorch doesn't track the computational graph. So you need to track the computational graph to be able to compute gradients. But that's expensive because it has to save intermediate values and things like this if you understand differentiation, autodiff. So by default, it doesn't do that, but we do want gradients with respect to this when we evaluate the velocity of the model. So for the physics loss, we need points over the whole entire domain. So we're going to do this lin space from 0 to 1, which is our modeling domain. And we're going to define 30 training points. Like this. And I'm going to do the same thing. I'm going to reshape this. And I'm going to do a requires grad again, because we're going to evaluate the PDE residual. Okay. Okay, good. So the next thing is to start training the PINN. So what I have here is a standard kind of gradient descent loop in PyTorch, very boilerplate. The most important thing is that I'm defining the parameters of my PDE. So this is the delta and omega naught, or basically the mu and the k values of the PDE, the coefficient of friction and the spring constant. I can change these values to make the solution higher frequency, for example, or more damped if I want. And then the other key point is that I'm creating an Adam optimizer in Torch, and we're going to pass it the parameters of the network. So up here, we created a fully connected network. And so this network has, one input, one output, because it's a 1D problem. It's got 3 layers and 32 units per layer. So we passed to Adam the parameters of that network, and then we've got a learning rate of 1 to the minus 3. Okay, so the next thing to do is to compute the boundary loss. So the first term is this term. So we just need to evaluate the network at 0, time equals 0. So it's very simple. We just do u equals the PINN at t boundary. And then we will say that loss 1 is just, I'm going to use a mean, but it doesn't really matter here because it's a single point. And then we'll do u minus 0 like this. And we'll do the mean squared value, just like we have in the loss. Who's with me so far? Yeah. Good. All right, so then it gets a bit more interesting. Next, we need to evaluate the gradient of the network with respect to the input to get the velocity. So we say du by dt, and this is where we're going to use autograd. And autograd is quite nice. All you have to do is you say, it's quite intuitive. You just say you want the gradient of u with respect to t boundary. And that's going to compute the gradient. There's another input where I'm not going to fully explain it, but you have to input a vector here. Can anyone tell me why Torch autograd needs that vector? It's a bit more advanced, but maybe someone knows.
Well, the gradients.
It's not to store the gradients, no.
Unit shape.
It's not to get a shape.
It seems like the data.
It's not the data type.
It is a starting point for automatic differentiation.
No. What, at the back?
For the
No. I can show you. Jacobians. So what does torch autograd.grad actually compute from a mathematical point of view? Jacobian? Nearly. Vector Jacobian product. Yeah. Yeah. So maybe I'll just show you quickly. So can someone tell me what a Jacobian is? Just anyone remember? If you have a u as a function of x, what's j? A matrix. Yeah. Yeah. So it's like a matrix, which is like the u1 by the x1.
Yeah.
What's the next one? Yeah, I think it's, I could be wrong, but I think it's that one.
I think it's the U.
Like this, and then the u1 dx. I always get it confused. Yeah. So what's the vector Jacobian product? It's a vector times by the Jacobian, right? So it's this. So this is actually what torch autograd does in a general sense, is it computes exactly this. So that vector is that torch.ones. So what I'm actually doing is I'm passing a vector here of ones. When I define here, this is the vector. So what does that actually look like for my particular setup? What type of function do I have here? How many u's and how many x's do I have?
From this code, it looks like
So what did I input to the pin? T boundary. How many points does that have? 1. Okay, so that's a single scalar value, right? What about u? What's the output of the pin? Also a scalar. So what does the Jacobian look like in this case? Yeah, it's just this. And so what's the shape of that vector? It's a one-dimensional vector. So we're just doing 1 times this. So we're just pulling out the gradient that we need. But you've got to be careful because this is a common problem or bug when people code pins, is they maybe don't fully understand what's happening and they get, in the general case, summations of vectors and columns of your Jacobian. So in this case, we just use ones and forget about it, but you should be careful with that. Why it computes the vector Jacobian product and not the Jacobian is a really interesting question to do with autodiff, but that's for another day. So, okay. So now we need to do, the second loss is torch.mean du by dt minus 1, because we want to make sure the velocity is 1. Yeah. Sorry, yeah, good point. I messed that up. Like this. So there's also one other argument I need to grab from torch.grad, which I need to say create graph equals true. I can't see with this. I also need to grab the 0th output. It's just because it outputs a tuple, but you don't need to worry about that. So the create graph equals true is just saying build the graph so that I can backprop through it again to get the gradient of the loss function with respect to the weights. So we need to keep hold of the graph. Okay, so now we need the physics loss. So we're going to do the same thing, same kind of code. Now we're going to pass the physics loss. And we're going to compute the first gradient. This is now with respect to physics. And we're going to compute the second one. And this is the cool thing, is we can compose autograd. So we can call autograd on autograd. And so we do the du by dt with respect to t to get the second derivative. Yeah, and that should all work. And then the final thing is to evaluate the physics loss, the PDE loss. So again, we're going to do a torch.mean. And now we're going to write the physics equation. So let's go back to the top. We need m. In this case, we're just going to say m equals 1. So we just need the second order derivative plus mu times the first order plus k times u. So that's what we're going to do. So it's going to be d squared u by dt squared plus mu times by du by dt plus k times mu. And then we're going to square this. Okay, and then I think that looks right. So now we're just going to evaluate the PINN loss. We're going to add all these loss values together. And then just standard PyTorch, we're going to call backwards on the loss function and then do a step with the optimizer. So I'm going to see if this works. No. Okay, so we need to figure out why. Only tensors. Yeah, I think I need a point. Okay, that looks promising. So what this is going to do is every 5,000 steps, it's just going to plot the prediction of the PINN, basically. But it's not right now. One like, okay, so I've got a few bugs. One's like. Oh, no, I did that wrong. One's like. Okay, let's see if this works. So it's creating that plot that I showed before. So the exact solution where the co-location points are, the boundary points, etc. So you can see already this has already taken 14 seconds to run. So it's really slow, just as I showed in the at the start. So let's see what happens. All right, cool. So it looks like it's training. So it's you saw how this trained already with the GIF. So it's the same code. Again, observations are it's fit the boundary condition first, and then it's kind of learning the rest of the domain afterwards.
And
yeah.
Can you summarize again the code that you wrote?
Oh, yeah, sure.
Kind of a bit faster.
So which bit? Everything or?
Yeah, like starting from you. No.
Here.
Yeah, here. Yeah.
Okay, yeah. So the first thing is you need the output of the PINN, the prediction of the displacement for the co-location points. So that's what that's doing. Then we need to take the gradient. We need to evaluate the gradient of the output with respect to the input. So this is where we use AutoGrad.
Yeah.
It tracked that original computation of the displacement, and then it computed the derivative of that computation. That's what AutoGrad did. And then we called AutoGrad again on that full first derivative computation to get the second derivative. And under the hood, like I explained, it's computing this vector Jacobian product. So then we have all those quantities at those co-location points. We collect them together into the PDE by timesing them by mu and k. And then we do the squared value and we sum to get our loss, our physics loss. So yeah, we evaluate each of our losses and then we sum them together to get our full physics loss, or sorry, our full PINN loss, and then we just backprop like normal. Does that make sense? Yeah. So it's not much different, honestly, to how you would write a normal neural network training code. The only difference is that you're using AutoGrad to get gradients. And then the rest of the code here is just plotting the PINN as it trains. I'm just querying the solution that it's learning. So yeah, after 15,000 steps, it's done pretty well. And this time it took a little bit faster than it ran when I benchmarked it, 74 seconds, so not too bad. Yeah, I'm running a little bit over, but I do want to show you this quickly. So this is the extension to use the PINN to do an inverse problem with this equation. So what we're going to say is, I'll just show you the picture. What we're going to say now is actually we have some data. We have some observations of the solution. So imagine we're looking at this oscillator and we're measuring, maybe with a bit of noise, the position of the oscillator as a function of time. And say that we know everything about it. We know the mass and we know the coefficient of friction, or actually we know the spring constant, but we don't know what the coefficient of friction is, like the friction from the air. And so that's the parameter that we want to discover from this data. Everyone understand the inverse problem? So this is really easy to do. You have the same thing. You set up a PINN. You set up the same physics co-location points. Now what we need to do is, instead of just optimizing the parameters of the PINN, like I said in the slides, we're also going to optimize mu at the same time. So we're going to hand both the parameters of the network and the mu value to the Atom optimizer. So I'm going to up here, I defined an optimizer. So what we're going to do here, we're going to define our optimizer here, but we're also going to optimize a parameter called mu. So we're going to say mu equals, and you can define a parameter, a learnable parameter in PyTorch by using torch.nn.parameter. And you can pass in, again, this is a bit annoying because you can't see what I'm writing. Yeah, you can pass in your initial guess of what mu is. So I'm going to say, I'm going to start with a 0 coefficient of friction. But because I've wrapped it in this parameter wrapper here, Torch knows that that's something that I actually want to optimize. And so when I pass my PINN parameters to my Atom optimizer, I'm also going to pass my mu value, and I'm going to say to the optimizer, you should optimize this as well. So how you do that is you just turn this, this is a generator in Python. You just turn this into a list, and then you add mu, you append it to that list. And so now you can hopefully see that the optimizer is going to optimize both at the same time. With the same learning rate as well. So then the for loop is basically the same. We're going to compute the physics loss just like we did above previously. So we don't have a boundary loss here. We're not going to assume we know what the velocity and the initial displacement is. But what we do have is these observational measurements. So we want to make sure that the pin fits these blue points. So I created these points up here. I called them U observation and T observation. There's 40 of them. So I'm just going to define a very simple supervised loss. So I'm going to pass my observational points into the network. And I'm going to say loss 2 is just torch.mean of U minus U observed squared. Can you see how that loss function is making sure the network fits the data that we have, the noisy data? I don't need to use autograd. I'm not doing anything fancy. It's just supervised learning with a physics loss. And then if I run this, so what this is now going to plot is on the left, the PINN's solution as a function of training step. It's also showing the noisy data that we have. And we're hopefully going to fit better to that solution as we train. But at the same time, that optimizer is trying to optimize that mu parameter, the coefficient of friction, and they're both going to change as the training progresses. So what you can see, and this is really cool, is as it trains, the PINN starts to fit the solution, fits the data, but the optimizer is also starting to converge to the underlying parameter, which in this case, I set it up to be 4. So yeah, you can start to see that PINNs are quite flexible. They can solve these like more complicated tasks where you have like some data, but you also want to do forward simulation and an inverse problem at the same time. So yeah, it's kind of interesting. It kind of overshoots, but eventually gets it. So and you can see it's starting to fit the data better and better. Yeah, so let's take, that's the kind of end of this session. So let's take a break. How long should we do? Okay, for everyone just joining now, so I'm just inviting everyone, if you would like to write a comment, you can write anything you want and you can vote, I think, as well. We've been talking about PINNs a lot, so you've probably got some thoughts on what the limitations are, so let's try and discuss them here. Yeah, this is awesome. I'll give you a couple more seconds. Okay, so let's have a look. So yeah, this is really great. I can tell that you've been listening carefully to my lecture and also Chris's. So things like they have spectral bias. Absolutely, we're going to be talking about that a lot. They can be very hard to converge. We don't know good convergence theories for many pins. Optimization is unstable. For discontinuous problems, they can be hard, just like they are for traditional numerical methods. What else do we have? Extrapolation. Yeah, they definitely don't generalize outside of the domain that they're trained on in their physics loss. Sensitive to hyperparameters, the scalar values in the loss. What else? Multi-scale problems, scalability, practical guarantees. Yeah, so I think you've pretty much nailed it. There's lots, basically. So let me just transfer. Okay. Right, so I think I might have summarized the big categories here on this slide that you just pointed out. Let me talk about the advantages first. We should be fair to pins. They're claimed to be mesh-free, although I'm not sure with the structuring of the co-location points we can say it's exactly mesh-free. But they do make a continuous functional approximation of the entire global solution. I think their biggest advantage for me right now is that they can solve these forward and inverse problems, or these kind of messy problems where you have data, you want to learn something about the underlying equation at the same time. That can be quite powerful. From an ML point of view, they're mostly unsupervised. We don't need data to train them, apart from the boundary condition. I haven't talked about this, but they can perform quite well for high-dimensional PDEs. Yeah, especially when compared to like finite difference or finite element, where they don't scale well with dimensionality. So the limitations is computational cost, because they use gradient descent. Challenging to optimize because they have a very nonlinear loss function. And coupled with that is that they're really hard to scale to higher frequencies. So this next session, we're going to really focus on computational cost. The next session, we'll talk about scaling to higher frequencies. And the specific approach that we're going to take in this session is a brute force approach. We're just going to try and use a maybe higher performant library to train the PIN rather than train the algorithm. So we're just going to look at JAX as a way to maybe improve the computational efficiency in a kind of brute force way. It's kind of my way of just teaching you JAX and showing you the power of JAX. I think this is just useful in its own right. So just to hit this home a bit harder, this is that PIN solving the wave equation that I showed you. Because this is a 2 + 1D system, this took way longer than 80 seconds. It took an hour on a GPU. Now, this was back in 3 years ago, and I didn't try too hard to optimize this, but you can get a feeling that this is just not scalable. The finite difference simulation would run in about 10 to 30 seconds for this frequency, so it's just not competitive. And what compounds pins, if you use a standard pin, is that you have to retrain them for a new initial condition. So you have to retrain the whole network to do a new simulation. There are ways to get around that. You can add conditioning inputs to the network and train across simulations and learn surrogate models, but I'm not going to get into that today. Okay, and yeah, just to reiterate, we're going to try and investigate what these papers said and try and see if we can improve the performance of pins. Okay, so what we're going to do is we're going to just re-implement. The goal of this session is to re-implement pins into JAX. So I'm going to go fairly quickly through this because you've got now a chance to do a practical. So I'm going to ask you to code that pin that I coded in PyTorch. I want you to re-implement it in JAX. That's going to be the practical session. So we're going to have a little less than an hour, but I think it should be okay. So hands up who's heard of JAX. Okay, and keep your hand up if you've actively used JAX. Maybe a third. And keep your hand up if you consider yourself a really experienced user or like had it over a year of experience. Okay, so that's maybe 3 or 4. Okay, great. So there's a real mix. I think a lot of people maybe have just about heard of it, but not ever used it. So that's great. I'm going to give you the basic introduction right now. So what is JAX? JAX is a Python library, just like PyTorch. And if you go to the JAX documentation, it describes itself as two things: accelerated array computation and program or function transformation. So those are the two core things of JAX. Now, the first thing, the accelerated array computation, that's basically saying we can run our code on GPUs. That's not different to PyTorch or TensorFlow. They do that too. But the second thing, program transformation, is a really neat idea, a very powerful idea if you can do it right. And I'm going to spend more time on that. So it turns out both of these things are incredibly important for scientific machine learning or scientific computing in general, even if you're not going to use machine learning. So JAX has become really popular, especially in the last few years. It's a library maintained by Google. And yeah, they now implement a lot of their state-of-the-art work in JAX. So Gemini, their foundation model, is built in JAX. Everyone know of AlphaZero or AlphaGo, the AI that beat the world's best Go player. That was all defined in JAX. It does Monte Carlo tree search, a kind of sophisticated search algorithm in JAX. We are using it a lot in scientific computing. Here's just a couple of examples. The AlphaFold model that does the 3D protein prediction is in JAX. Brax is a whole simulated environment for reinforcement learning in JAX. And then Neural GCM is a very recent state-of-the-art hybrid scientific machine learning model for weather forecasting. So it has a ODE solver and neural network components trained in JAX. And this is another example of a paper that did a really fine scale global climate simulation in 24 hours with 16 GPUs, A100s in JAX. So it definitely lets you do compute at that scale. Okay, so let's talk about the first part of JAX, which is just simply accelerated array computation. So what's amazing about JAX and what makes it very accessible to start with is that they just rewrote NumPy. Hands up who is familiar with NumPy? Yeah. Hopefully most people, if you've done Python or PyTorch. So JAX.NumPy is, I don't know if it's a superset, but it's basically a like for like of all the NumPy functions. And actually, in some cases, when you want to convert from NumPy to JAX, it can be as simple as just swapping import NumPy to import JAX.NumPy. And your code can just run immediately on the GPU. So we'll get onto the program transformation in a minute. Oh, sorry, I'm going the other way. Yeah, so like I said, you just literally switch your import statement from import NumPy to import JAX. And then the interface feels very, very familiar. They try and maintain it exactly the same as NumPy if they can. So you have a JAX array. You can do all the fancy syntax stuff with JAX. So you can do your @ symbol for your matrix multiplies. You can print the array. You get the same result. Now, what's cooler is that this, by default, if you've installed JAX into a GPU environment, so like on a Linux machine or something like this, this automatically runs on the GPU. Who gets annoyed with torch.device? Yeah, so there's no devices here. It just happens. It doesn't. You don't need to tell the array what device it's on. You just think of it as an array, and the hardware is just managed by JAX itself. There is, of course, ways where you can switch devices if you want, but by default, it will just run on GPU. And fast, real fast. So this is what I did here is make these arrays massive. So I did a 10,000, 10,000 by 10,000, 10,000 matrix multiply. On my laptop, it ran in 7 seconds. On the GPU, it ran in milliseconds, 50 milliseconds. So anyone just tell me why is this actually faster on the GPU? What's the actual reason? Yeah. Okay, GPUs are set up to perform matrix multiplications. So what is it about a GPU that makes it good for matrix operations? Say again. They do the computation in parallel. And how do they do that? Multiple cores. Yeah, so CPUs have multiple cores, so what's the difference?
No, the difference in numbers is huge.
Yeah.
You have like 4, 8.
Yeah. GPUs have thousands of, or if maybe even tens of thousands of cores. So this is what the CPU looks like at a high level. You've got maybe 4 or 12 cores, really designed for like serial processing at low latency. So like flipping between different programs serially, which is perfect for like running an operating system, but not perfect for matrix operations. Whereas GPUs have, you can just think of it as thousands of cores, and each element of the matrix operation is done on a separate core. So each multiply is pushed to a different core. So you get amazing parallel throughput of these GPUs. Hopefully that makes sense. It makes it obvious that GPUs are really good. Okay, so here's an example. I had this existing wave simulation code in NumPy. So it does, you can't see the code, but don't worry. It's what it's doing is a very minimal finite difference simulation. So there's a for loop here where it's doing a finite difference step of a wave field, and we're starting with like a Gaussian source or something like this. Fairly high frequency, like a fairly decent computation. You see at the top, import NumPy. Okay, just swap it to JAX. Now it runs in JAX. That's pretty cool. And what you can see is the core of this finite difference code is just a bunch of matrix operations. You have your discretized mesh of your solution. It's a 2D thing. And you're doing lots of difference calculations at every point on the mesh. That's a matrix operation, like a difference operation of two matrices. So you should, alarm bell should ring and be like, that could be parallelized massively on a GPU. And like I said, I don't need to switch devices. If I just install this on a GPU, JAX will start running this code on the GPU. So
for example, you have a cluster and then you try to compute the speed ups with respect to the number of GPUs.
Yeah.
What is in the plan?
Yeah, so there's just single GPU acceleration, and then there's multi-GPU acceleration. JAX will let you do the multi-GPU, and it's quite easy as well. I don't have the time to talk about it. I haven't done those benchmarking. I think it depends on the program and how much communication you need between GPUs and things like this. But
One expect, let's say, linear.
it really depends on your algorithm. But if it's like embarrassingly parallel, sure, yeah, that's the goal. Yeah. So yeah, the code is basically exactly the same. There's one small difference, which I'm not going to get into. We use a slightly different for loop in JAX to make it easy for JAX to understand. But yeah, the time difference is incredible. So NumPy on the CPU, 8 seconds. If I use JAX on the CPU, so I can just run JAX on my computer, that already runs 8 times faster. And JAX on the GPU is 123 times faster. Same code, just faster. The other thing you might notice if you're reading carefully is I'm doing what's called a JIT compilation. So I'm going to talk about this in a minute. This is just-in-time compilation, and this is one of the program transformations of JAX that makes your code faster for you, basically. Okay. So we're going to skip this because I want to give you more time. So the next thing we're going to talk about is this other really powerful part of JAX, which is its program transformation. Okay, so this is the core concept that you need to take away when you want to start using JAX. Okay, what is a program transformation? So program transformation, we can also call it a function transformation. And so what I've done here is I've written a really basic function, f of x equals x squared. Right. So this is where the magic of JAX happens, is in these so-called program transformations. So imagine I want to turn that f of x squared, or f of x equals x squared, into its gradient function. So I want to instead return 2x instead of x squared. So what I want to do is I want to start with a Python function that gives me an output, and I want to convert that to a new function that gives me the gradient. That's a transformation, a gradient transformation. Everyone with me so far? So what JAX has is this thing called jax.grad. You can think of it as a black box. It's super clever how it works under the hood. But what it does is it's a function, another Python function, that takes a function as input. So it takes my native Python function, f, and it returns another native Python function as the output. But the only difference is that that new function has been transformed. And specifically, jax.grad transforms that function into the gradient of the original function. Does that make sense? Yeah. Yes, if the function is not continuous, it really depends exactly what you mean by it not continuous. So then that will depend on exactly how you defined that function. So if you've defined like a heavy side or a step or something, then that transform function will give you the gradient where it's not 0. And then it really depends on how you define that discontinuity. So it depends how you implement it. So if you use jax.numpy.heavyside, I don't know if that's actually a function, but I think, or neural network.heavyside, then this is behind the scenes. When Jax calls grad and it does that function transformation, it will account, for that discontinuity somehow, whether you want to take a left side or a right side or an average or whatever you want to do. So but you can define that. You can say how jax.grad should transform your function if you want. Okay. Yeah, so remember, this is the key difference to PyTorch, is there's no behind the scenes computational graph. Nothing's happening behind the scenes. You're literally just being given a native Python function that you can call just like normal with any input you want. So I take my df by dx function and you print the value at x equals 10. And again, I'm just pushing in arrays. There's no requires grad or leaf values or grad values or anything like this. Nothing. It's just transparent arrays. And as you expect, if you print the function, you get 10. If you print the gradient, you get 20. So it's pretty powerful. So what's interesting is what's happening under the hood. And jax.grad is reading your function, like the lines of code that you actually wrote. It's taking that as the input. So it's reading your function, and then it's going to rewrite that function into the new function that evaluates the gradient. And when it reads the function, it doesn't just stay in Python code. It actually converts it into a lower level representation, which is called a JAX PR. It looks a bit more like machine code. It's not machine code, but it's harder to read. But you can actually use this JAX PR function, and that will just print out the low level code version of your function. And you can kind of see that it's doing x to the power of 2 and returning the value. Like you can kind of see that in the code. So after I've applied jax.grad, I can do the same thing. I can say, what's the low level code look like for that new transformed gradient function? And you can see, sure enough, there's a bunch of overhead stuff that's happening. But if you look at the outputs, it's doing 2 times by the input, which is exactly what the gradient function should be doing. If you differentiate x squared, you get 2x. So can you see how JAX is actually giving you a function that you can evaluate any input, and it's really the gradient function. Okay. So that's the key idea. Program transformation is transforming one program to another or one function to another function. It treats programs as data. The transform converts a program to a program. And it's also known as metaprogramming. It's a whole kind of paradigm of programming where you have programs that write programs. So it's, yeah, really fascinating to study that more. Now, a really, really powerful thing in JAX is that these outputs of these function transformations, like I said, they're just another Python function. And what that means is JAX allows you to arbitrarily compose different function transformations together. You can chain them up. So you could do a grad on a grad. So this is what we're doing here. We're taking our new grad function and we're just doing jax.grad again. That's going to give us a new Python function that if we call it x equals, say, 0, what number are we going to get? 2. because the second order gradient is 2. It's constant value.
This would make it sequential, right? Because like.
Yeah.
Have to make sure the.
Yeah.
From the first composition.
No. So it's not sequential. So remember, df dx and df dx squared, they're 2 separate functions. So I can just call one or the other in my subsequent code. I could even just throw away df dx and just call df dx squared with the value of x. It's just a function.
Yeah, but that would in turn call df dx.
No,
Internally in the transform code,
Yeah.
it would be doing autograd. So you do need to compute this. It does need to compute it internally in the function. Yeah. Yeah. But again, that comes down to what autodiff method are you using. And there's lots of options in JAX. So yeah.
Now, still, involved in Python overhead, right? I mean, do you prefer JAX over Julia language, for instance?
Yeah, so I'm not an expert in Julia. I haven't used it very much. So I'm not the best person to ask about that actually. I think Julia is a great option, and I know a lot of people are really excited by it as well. So I would just encourage you to do your own benchmarks and test. But specifically with the Python overhead, the answer is no, because JAX doesn't wait for the lock, the Python lock. So everything is done asynchronously. So when you call a function, it jumps to the next line of the Python code before evaluating the tensor, and it only waits when you actually need to use the tensor. So you can look at the JAX documentation. Yeah. Okay, so I'm not going to go into detail, but there's another reason why I like JAX is instead of just doing backprop, you can do all sorts of flavors of auto differentiation. There's forward mode, there's reverse mode, you can evaluate entire Jacobians, you can do a lot of things, Hessians. I'm not going to go into it, but everyone is just another gradient transformation. Sorry, a function transformation. Okay, so this is just one type of function transformation. Can you think of other function transformations that we might want to do? Can anyone think of a different one? Compose? Yeah, so you can compose 2 functions together. Yeah, that's one way. Yeah, that's pretty simple. It's just a function calling a function, but it is a transformation. Any other ones? Integral? Yep, absolutely. So you can evaluate integrals. Right. So I'm going to give you 2 more examples of very important transformations. One is automatic vectorization. Hands up who's heard of this, or vectorization in general. NumPy actually does this, vectorization. So this is taking a function. So this function here, f of x and f of w, b, and x is doing what one layer of a fully connected network might do. Basically taking a single value, x, timesing it by a weight matrix and adding a bias. So one thing you might want to do with that is to batch the network or the layer across multiple examples, multiple inputs x. And if you were going to do that in NumPy, you would have to increase the dimension of your array. You'd have to think about broadcasting and all these complicated things in NumPy. But actually, that vectorization is just another function transformation. You could imagine another function where the input x has an extra batch dimension, and it does the equivalent of a for loop of the original function. That's called a vectorization or a vectorizing map of the original function. So yeah, so what's cool is you might write a function where you're just thinking about a single example, but then you can vectorize it and create a new function that works over batches of examples like this. And yeah, so JAX has this function transformation. It's called a VMAP. Same idea as the grad. It takes a function as input, this original single x input function, and it outputs a new function which evaluates it across a whole batch of inputs, where x batch now has an extra leading dimension in the tensor. There's one other keyword argument, which is this in-axis, and it's just saying which of the input arguments should I batch basically, and which dimension of the input should I batch over. So here we just want to batch over x, and we're going to say the batch of points is going to be the first dimension of that bigger tensor. Who's with me? That's a little bit more sophisticated, but hopefully you get the idea. Okay, so yeah, so if I call the function for a single point, I get 11, but if I call the vectorized function, I get the function evaluated over 3 different points, all at once. Yeah.
So instead of 0, I can put 1 there. Will it be compilation error?
Yeah, probably. Yeah. Or maybe not. I'd have to. Depends on the shape. The shapes. The shapes have to match still. So what's more interesting is, again, if I use that JAX make PR string and I look at the low-level code that it's transformed my code to and from. A naive way of doing VMAPs is just to write a for loop, right? You just loop over the inputs and you just you concatenate them together at the end. But that's sequential, that's not going to maximize the GPU. What we really want to do is batch on the GPU. We want to push all these batches onto cores on the GPU and do everything in parallel. And that's what VMAP actually does. And that's what makes it so powerful, is that it thinks really carefully about these vectorizations and goes down into the GPU level and turns them into actual vectorized computations. So for example, here, when you've got this batch operation of X with a weight, this is a matrix operation, and you can do each of these elements element-wise multiplies on a core, rather than do a for loop, wait for each element. And if you look at the low-level code, it's actually doing that. It's doing this generalized dot product, which is GPU compatible, basically. So it's really powerful. It's not, there's no for loop in this transform code. Yeah, much faster than the Python for loop. Okay, the final transformation is what JAX calls JIT compilation or just-in-time compilation. It's called just-in-time because it's not done a priori. You don't compile your code and then run it. It just compiles as when the first time you call the function. So it's kind of like a lazy compilation. And you can just think of this JAX JIT as just rewriting your code to be faster. So you can just jax.jit f, it will give you a new function that evaluates f, but it's just somehow faster. You don't need to know anything more than that. But if you're interested, it does stuff like this, where if you imagine this function is like x plus x squared plus x cubed, a naive way to do that on a GPU, GPUs have like a global memory, and then you have these cores. You might start with your input on the memory. You might push it to a core, do an x squared, save it back to the memory, then do an x cubed, then save it back, do an x to the 4 or whatever it is, or a summation. But that's inefficient because you're doing a lot of communication between the memory and the core. And so what JAX JIT will do is it'll be like, oh, I know a clever way of doing this. I'm going to read that function and rewrite it to one that just uses the global memory once and uses all the operations on a single core. And this is much faster. So this is called kernel fusion. This is a trick that low-level CUDA programmers might be very familiar with. You can get big speed ups of neural networks. You know, these people that really super optimize LLMs, this is what they're doing on the GPU, is fusing operations on the core. Yeah, and it makes a big difference. So this exact example runs 8 times faster if I do a JIT compilation. This is on my CPU, so it's doing a CPU optimization instead of GPU optimization. So yeah, JAX is clever. It knows how to optimize the specific hardware that you're on as well. Okay. Yeah, I'll skip this. So yeah, there is an ecosystem of built around JAX. So the big difference most people realize when they start with JAX is that it doesn't have a neural network library like PyTorch neural network. Instead, there's a few options. They're kind of third-party libraries. So it's a bit lower level to get started with, but good options. I like to use Equinox, but there's also Flax and other methods as well. The main also optimizers, there's not a built-in optimizer. So Optax is generally the module that's used. And then there's a lot of other modules for SciML. For example, Diffrax lets you define neural ordinary differential equations, if you know those. Lineax is for linear systems. Jax.scipy has a lot of scipy's methods for linear solvers and things like this. So there's a lot going on. DepexDE is worth mentioning. That's a PINN library if you want to train pins with a high-level library. I just want to showcase one thing, which is Optax. This is optimization with JAX. So remember I showed you right at the start that forward simulation code for the wave equation. all I did was import jax.numpy instead of import numpy, and it did the whole thing on the GPU. Now all I have to do is write a few more lines, and I can optimize my simulator. And specifically, I'm now going to use it to do an inverse problem. You can imagine I give you these observations of the wave field, you know, the seismic amplitude, and I want to figure out what the underlying velocity model is. I can use jax.grad to get the gradient of the difference between my prediction of my simulator and the data with respect to the velocity model, the input to the simulator. So that's what this jax.grad is doing, my sum loss function based on the data with respect to the velocity. And then I'm using Octax here. This is the Adam optimizer in Octax to optimize that with respect to the as in a for loop with gradient descent. And so like in like 6 lines, I've gone from doing forward simulation to like full blown, in the seismic imaging world, we call this full waveform inversion, a really sophisticated inverse code basically. And it's running on a GPU and it runs really fast and it gets a nice solution. So yeah, anyone know why it only learns the circle and not the velocity around the outside? Anyone got any physics intuition? Did someone say?
You only have data.
Yeah.
So
Yeah, there's only the wave field is only, it starts in the middle and propagates out to this boundary. So there's literally no information, no gradient information in the surrounding velocity model. So it's kind of interesting. Okay, so I'm going to skip this, or just say very briefly, JAX is a lower level library because it uses these function transformations. And so there's these things you need to look out for. When you go through the notebook, you'll look at these a bit more. Yeah. So yeah, now we're going to move on to the practical. We have 40 minutes until 12:30. So that should be enough time, but we can maybe do a little bit more at the start of next session if we need. And your task is very simple. I want you to take that PINN code that I wrote in the first practical and simply rewrite it in JAX, like for like. So we're going to use the same hyperparameters, collocation points, everything's the same, network architecture. And we're going to see if you can achieve that faster goal by using the JIT compilation and the VMAPs and everything else in JAX. So if you can go to the, let me switch screens. If you can go to the, let me just close this. I don't know if this is going to work. Okay, I'm going to have to find the session again. Let's go to here. Yeah, so if you go back to the GitHub repo and then scroll down, and if you hit session 2, practical. So there's 2 parts. The first is just a basic introduction to JAX. So you're going to be using the VMAPs and JIT compilation. And then the second step is to write, well, you're going to use that basic JAX to do basic function fitting. And then the final step is to then train the PINN with that JAX code. So I also want to introduce Job, where, yeah, at the back. So Job is Victorita's PhD student, I believe. Yeah. So he's been really great. He's already looked at the practicals in the last week, and so has good experience, I hope. So we're both going to walk around and help you with your code in the next 40 minutes. And yeah, any questions, just raise your hand and let me know. Hopefully you've managed to get into this now and train that same PINN that I trained in PyTorch in JAX and re-implement it in JAX. So yeah, we were trying to solve the harmonic oscillator, and I hopefully set up the code so that it uses the same setup, so the same collocation points, same lambda values, same learning rate, etc. And there was a couple of tasks to do. So the first was to define the fully connected network in JAX. And I wanted you to complete this forward function. So this is what you would do in PyTorch. You would write your forward function. The only difference here is that we did it a bit lower level. So I actually initialized the weight matrices themselves rather than define like a linear layer. So I wrote this function already. This one uses jax.random to give you your random weight and bias matrices and vectors. And then the forward function. So this is the key thing to realize here in the forward function is, unlike PyTorch, the input to the forward is a single point. It's not a batch of points. This is the key kind of philosophy in JAX, is that we deal with single point functions and we use VMAP to batch them. So yeah, X should have just a shape of 1, a single point. And then we just go a for loop through our layers. We use not jax.numpy dot product to do the matrix vector multiply, add the bias, apply the activation function, and run through no activation function on the last layer. And the output should be that it's still a single value, because the final weight matrix has one output, basically one hidden one channel. Hopefully that makes sense. Hopefully it's very simple to write. You just need to use NumPy. There's no fancy JAX stuff going on here, really. So then we just plot the output of the untrained network. So we're going to start with a random key. You probably noticed by now that we do explicit random state management in JAX, which is a little different to NumPy and PyTorch. So we have to carry around the kind of state of the random number generator. So we initialize the network with three layers, 32 hidden units. And then we create a batch of test points. And this is where we're going to use jax.vmap to batch our forward function over that batch of points. And we're going to specifically batch just the second argument over the 0th dimension of that input. So that's what that's saying is we want to apply the same parameters for every point, and we just want to run the forward function over these batch of points. And you can see here the batches in the first dimension of that T test batch tensor. Okay, so the untrained network looks like this. It's kind of interesting what neural networks initialize to. It's a pretty flat function. Okay, so then we're going to train the network. So we need to evaluate this loss function just like we did with the PyTorch implementation. So I've got two functions here. One is evaluating the physics loss, and the second is evaluating the boundary loss. So the physics loss has to compute this physics term over this batch of co-location points. But again, the JAX philosophy is that we should define this physics loss for a single co-location point, because you can imagine we want to call this PDE residual over a batch of points, and we want to do the same computation over each TI before we do the sum. So we can write this kind of inner residual computation as for a single point and call it many times and then sum it. So yeah, T here is an individual point, and then these are just the parameters of the PDE and the parameters of the network. And this function here is just a little helper function to remove the dimensionality of T. So T is of shape 1, which we can just flatten to a scalar. And that just makes it compatible with grad. So jax.grad expects you to have a scalar, not a shape of 1, because that's in JAX speak not quite a scalar. And then we just call the jax.grad on these scalar functions, doing the two transformations, composing them together. So jax.grad and then jax.grad again to get the second order derivative. Remember, jax.grad is giving us the function, so then we have to call the function to get the actual value. And then we just compute the residual, the mean squared value of the residual this is for a single co-location point T. So this is going to have a shape of, it's going to be a scalar value. Any questions so far? Does that make sense? Yeah.
How do you compute the mean when you pass?
Right, exactly. So we're going to get onto that. How to compute the mean over the co-location points? Good question. Yeah. Before I get to that, let's just talk about the boundary loss. So it's very similar, same inputs. Again, for a single point, the boundary loss for this particular case is just a single point anyway, so we don't need to do any batching in the future. So this is the same. We're isolating the function. We're calling grad, and we're computing now the the two boundary losses on the velocity and on the displacement. So very similar, the two losses, the displacement loss and the velocity loss have, again, as scalars, because we're just dealing with a single input time point here. Okay, so to answer your question, how do you deal with the mean? So this is where we now define the full PINN loss function. And it's now going to take in, again, that single boundary point, because we don't want to evaluate it over many points for the boundary. But now we're going to give it a batch of physics points. So these are all of our collocation points, where the batch is in the first dimension of this tensor. So you can see here, it's going to have this shape n by 1. So n is the batch dimension. So what we need to do is we need to compute the physics loss over this batch. So we're going to do a VMAP over our physics loss, which was defined for just a single collocation point. And we're going to map over the 0th dimension of T physics batch. So can you see how that's going to give us our batch of residual values, our residual squared values, basically, for the batch of points? So that's basically, if we look at the equation, it's going to give us everything apart from the summation. So, you know, the squared values of all these residuals. So the final thing we need to do is the mean here, basically. This is a mean. So that's very simple. You just do numpy.mean on that array, and you end up with another scalar. So that's your full physics loss scalar. We can just call the single point for the boundary loss, because in this case it's just a single point. You get your other two scalar losses, and then you add them up with the appropriate lambda values that we used in the PyTorch example. And then that gives you your final kind of scalar loss value. Does that make sense? So now we've got a loss function here. This is our main loss function, where it takes in the parameters of the network as the first argument. So just like you did with that polynomial regression example, we can now just do value and grad on our loss function with respect to the first argument, which is the parameters here. So that's going to give us the gradient of the loss with respect to the network's weights. And then we're using optax here. So rather than write our own gradient descent step on the parameters, we're just going to let the Adam optimizer of optax do it itself. So this is very standard optax code to do that. And you can see it's just computing that gradient and then you know, computing an update to apply to the parameters. Basically, that's all it's doing. The rest of the code is very boilerplate. Looks very much like the PyTorch code. You know, you're defining your collocation points, your physics points, your ODE parameters. This is the same as we did in PyTorch. You're defining your test points. You're defining an optimizer. This looks quite similar to PyTorch again. And now we just have our for loop, which is our gradient descent, and we're just doing a step every step of the for loop. And you can see when we call the step, we're going to be updating the parameters and then passing them back into the step function to you know, change the parameters. Yeah, and then the rest is just going to call the same plotting library as we had before to show what's happening when we train. And what did people find? Did it train the same way as the PyTorch, roughly in 15,000 steps to about the same accuracy? Hopefully, I think it should have been the same roughly. And what times did we get? Maybe someone can tell me. Did anyone get close to 11 seconds? 10 seconds, yeah. Cool. So are you convinced that with you know, comparing PyTorch to JAX for this particular problem, we have a faster code? It's pretty, so that, and the reason is probably the JIT compilation and the clever automatic vectorization to make, you know, efficient code. Yeah. Someone pointed out earlier, PyTorch does have a JIT compilation thing, so maybe it's not completely fair. I would like to see that comparison too. And it also, yeah, so there's now PyTorch functional. It's like a new update that came out in PyTorch 2 or something. So yeah. So did anyone manage to get to these extension tasks? Hands up if anyone. I know it's a big ask. Oh, a couple of people. Which one did you try? Could you tell me?
Yeah, so I tried to increase the frequency.
Yeah. Yeah.
Without changing anything else, and plus struggle with it.
Yeah. Yeah, so that's the big one, is how can you change the omega naught? And what you'll find is that it takes a lot longer to train. And that's because of spectral bias. So that's what we're going to talk about next, basically. So yeah, I really encourage you to have a look at some of these tasks if you have time later. It's very useful to test these hyperparameters and settings. Okay, so if you give me a couple of seconds, I'll just go back to the slides. Yeah.
So that even index is also possible then. Meaning but
Yeah. Yeah.
It also like straightforward.
Yeah, so that's a good question. So just to reiterate, the question was, can you use mini batches to train the PINN? And it's very easy to do it in PyTorch. You can do your data loaders and shuffling and stuff like this. So the cool thing is you can use data loaders in JAX as well. You can literally just import a data loader, and in the for loop, iterate over the data loader, and it will give you new X batches. And so then you just pass that straight into step, and you're done. So yeah, that's very simple. Yeah. Okay, cool. So we're moving on to the last kind of session, and this is where we really get to these kind of state-of-the-art methods to really improve the performance of PINNs. So let's go back to this slide. We just looked at computational cost, and we tried a very brute force approach, which was just to switch programming library from PyTorch to JAX. And we got a modest speed up, and that can be useful, but that's really not changing the underlying algorithm to improve its inherent scalability. And so what we need to really think about is how to change the definition of the problem to start with to get those kind of millisecond speeds. And so that's what we're going to talk about in this lecture. And you've got another practical where we're going to, actually get rid of the gradient descent altogether and use a least squares solver instead, and that will be much faster. So what I'm going to start doing is just, instead of just talking about computational cost, I'm actually going to talk about challenging the difficulty of scaling PINNs to high frequency problems, and how we can kind of overcome that. So I did a very, very simple test for PINNs a long time ago, where I took maybe the simplest possible ODE I could think of. So du by dx is cos omega x. And I solved it with a PINN, standard PINN, fully connected network. And I tested it with different values of omega in the equation. And I wanted to see how PINNs scale with frequency. And so on the top left, I started with a very low frequency. Omega is 1. And yeah, basically 2 cycles of the solution. And I could train a PINN with 2 layers, 16 hidden units. So basically 321 parameters, like quite a small model. And it trained with this convergence curve here, this red one. So in maybe 10,000, maybe 5,000 steps, and got down to maybe 10 to the minus 4 in terms of L1. So a pretty good approximation, not amazing in traditional terms, but still pretty good. And the issue is, as soon as you increase the frequency, the PINN starts to really fail. So the top right is all I did was just change omega from 1 to 15, and I used everything else is the same. So I used the same neural network, and it's really interesting actually. What you find after training is that the neural network only fits something like 2 or 3 or 4 of the cycles of the solution. So can anyone tell me why it's only fit 3 cycles? What's gone wrong with the model? Yeah. Actually, I think maybe I made one mistake. I think I did increase the collocation points so that I had the same number per cycle. So it was like below the Nyquist frequency, whatever, or above it. So that's not the problem. Anyone else think why didn't this train this particular PINN? it looks like it's really accurately got the first few cycles, but then it just wasn't able to get the cycles afterwards. So why is it struggling? The weights, yeah. Symmetry, maybe. I think actually the answer is that there's just not enough weights. Yeah, it's that. Yeah, the network is not expressive enough. So remember we were saying ReLU networks are like piecewise linear. So there's only a finite number of linear pieces. So if you're going to approximate this bigger, more cycles, you're going to need more pieces, which means more parameters.
Take it outside the training set as well.
Yeah, kind of. It does have co-location points like from -6 to 6. So we are trying to force it to fit the whole domain. But for some reason, it just starts in the middle and gets stuck there. So that's kind of interesting. So what I did was just ramp up the number of parameters. I made a bigger, deeper network, more hidden units. And my first attempt with 4 layers and 64 hidden units was kind of there, but didn't get all the cycles. I found I had to go all the way to like 5 layers, 128 hidden units. So this is now a model with 66,000 parameters. And even still, it's got all the cycles, but the ones on the edges are really poorly approximated. And if you look at the gray line here is the convergence curve of that bigger network, and it's thrashing around all over the place. It's really not happy. Yeah.
Curious, did you ever try adding like using small networks with sinusoidal positioning embeddings?
Okay, yeah, great. So you're already thinking steps ahead. So let me summarize. Basically, it doesn't feel like the fully connected network is an appropriate architecture for this problem. And so, yeah, for sure, you can do things like like Fourier input features or sinusoidal embeddings, and that definitely works on this problem. And that's a whole direction as well to take. But the vanilla PINN is just not suitable for this problem. Yeah.
I think that's a boundary condition as well.
I think it's the boundary condition, yeah, like you said, yeah. So I said u at t equals 0 is 0. So maybe it's this thing where I've weighted up the boundary a little bit too much and it's snapped onto that first and then tried to fit around that. That's probably what's happening. Yeah.
It also feel like it captures the frequency well for a certain region, but
Yeah.
I don't know if I expected it to like not capture the frequency well, like capture a certain number of modes, but not the full mode.
Yeah, it is interesting that it like does get the cycles well where it models cycles. So yeah, I'm not sure the reason. Yeah, it's interesting. Could be to do with the activation. So I'm actually using a tanh activation.
Yeah.
Yeah, I'm not sure. Okay, so Chris talked about this a lot, and this is a well-known issue that contributes to this problem. It might not be the only reason, but spectral bias is a well-known property of neural networks, even without PINN losses. So just supervised learning. So this is, for example, in a completely data supervised way, fitting this neural network to a multi-scale function of like multiple frequencies. What you typically find is that the network tends to converge on the lower frequencies much faster than the higher frequencies. And there's loads of great work looking theoretically and kind of showing convergence rates with certain assumptions. And so this is actually really good for machine learning in many ways, because hands up, who knows of early stopping? Yeah, so this is like a standard technique we use where we stop the model training early to avoid overfitting. So can you see how you would, you might overfit the data if you carried on training, if you just wanted a smooth regression. So that's pretty good for like big over parameterized machine learning models. But for things where we want to solve PDEs precisely, it's really bad. Yeah, so this is my example of the harmonic oscillator that we've been looking at all the way through. All I did was increase the frequency like you tested over there. And what you see is this sort of behavior. But this is now 15,000 training steps and it's barely got the first cycle correct. And just imagine if I doubled the frequency again, like that's just it's not happening arguably because of spectral bias. So there's other things that are even worse. this is not the full story. So this is, by the way, this is very empirical, back of the envelope. This is not formally proved at all. So big like flag on that. But this is often what I see when I train pins empirically, is that the cost, so imagine increasing the frequency. First of all, you need the fundamental physicist or information theory brain says that you need enough co-location points to sample the Nyquist frequency. So that just basically means having like at least 2 points per cycle or something like that. So if you've got, this is a 1D problem, but if you've got D as your dimensionality, then your number of co-location points is going to scale like omega to the D. So you need that many co-location points as higher frequencies are added. You also, just like I showed before, you need a larger neural network. You need more parameters. I don't know how many more, whether that's a linear dependence on the frequency or not, but let's just assume it's some function of omega. And then you've got the effect of spectral bias, like compounding that on top. So then you've got like again, I don't know what the function is, but some S as a function of frequency. And so you would factor all these together and you get this sort of big O notation. And then you compare it with like a finite difference scheme. And of course or a finite element scheme. And of course that depends on the PDE or the particular problem. But for this problem, a 1D time dependent ODE, I can for sure write an FD simulator that would scale like omega to the D with a simple time stepping. So, we have to address both of these factors to come anywhere close to this finite difference method. And that seems like quite a big ask. So yeah, you have a question. Yeah. Yeah. Maybe. Yeah, maybe. I think it's still, I don't know if it's, you could, I'm not actually sure of the theoretical results here, but I imagine that even if you have a single frequency, if it's high frequency, it will take a long time. It doesn't need to be a multi-scale solution. It's just the fact that it's high frequency is difficult. By the way, this doesn't precisely have a single frequency because it's a modulated function. So there's a bandwidth there. So yeah, does this make sense to everyone? It's quite important to, because this is true for pretty much any pin, I would say, regardless of the problem, it grows super linearly with the frequency usually.
Generally, your condition will fall around.
Yeah.
You can put in the matrix, it's not something.
Yeah. Yep. Okay, so we're going to try and get away some of those, or like cancel out some of those factors with some improvements to the pins design. So we're going to be talking about using domain decomposition with pins. So this is just one idea. Someone mentioned Fourier features. There's loads of other stuff you can do, but this is what we've worked on. So I really want to show you it. And it's a very simple concept. And it's basically to say, instead of having a single neural network for the entire global domain, we'll split the domain into many small parts, subdomains, and then put a separate neural network in each. And our hypothesis is that by doing that divide and conquer kind of strategy and training each subdomain network instead of a global network, that becomes like a smaller problem in each subdomain. It is somehow still coupled, but that resulting problem is easier to solve. So this was probably the first, or at least one of the very first papers that did domain decomposition with pins, called XPins. So they did exactly what I just described. You can imagine a complicated boundary here for your modeling domain, and then you draw equally complicated boundaries, like subdomain boundaries, and have networks in each. I'm going to tell you about our method, which is slightly different. We call it FB pins, finite basis pins. So the only difference really is that we use an overlapping domain decomposition.
Like ghost cells.
Say?
Like ghost cells.
Cells.
Similar to like
Yeah.
MPI or something. Parallel programming.
I'll get to that. But yeah, you can do parallel methods. But let's just imagine this like 2D rectangular domain. So we might just split it into a rectangular, uniform rectangular domain decomposition, where each little rectangle is like overlapping with its neighbors. And what we do is, like I just said, we take an individual network and we put it in each subdomain. And then the mathematical expression for the solution, when we use an FBPIN, is we say that the final solution over the entire domain is just the summation of all the individual solutions from each subdomain. Yes, so mathematically, it's just a summation over all of your J subdomains. And you take the neural network J here as the subdomain in each network. Everyone with me so far? Okay. So there's a couple of other tricks that we do that are very important. So one is that we restrict each neural network to its own domain. So we don't let it have a value outside of its box. And we do that with what we call a window function, which is this W here, or omega maybe. And that is just a local function. It could be a Gaussian or a cosine or something with local behavior that says, yeah, outside of that domain, the value of the window is 0. Yep. Say again.
Are they learnable too, or are they fixed?
They're not learnable, but they could be. So that's the active direction of research. Other people are doing this. And the other trick that we do is really important is we normalize the inputs to each subdomain separately. So the best practice with neural networks is you normalize your inputs between -1 to 1. But imagine we're in this subdomain here, and we get a point in this box. We normalize that point so that it's -1 here and +1 here. So we normalize on the subdomain boundary. And that's really important. That step basically, you can imagine having a high frequency function, but maybe like it has 4 cycles along this dimension. But here it would just look like a single cycle. And then so the network only has to model like a single cycle there. And what that really is doing is alleviating the effect of spectral bias. It's like shrinking or stretching out the function or the frequency to a lower frequency. I've got a 1D example, which is a bit easier for you to understand. Yeah.
So what's the overlapping ratio in like 10%, 20%?
Yeah, so it's interesting. I'm not sure why, but it's useful to have a fairly good overlap. Yeah, 50% can be a good number. You need to have communication between the subdomains. This is a traditional domain decomposition methods. If there's no overlap, then but you have to have some communication somehow. Yeah. Yeah. So the way that we do the communication is through the overlapping regions. The networks all provide answers that get summed together. So there's that pushes information through all the networks together.
So my second question is again this one is not. So if you have this overlap,
yeah,
you are, for instance, NN0 will do answer for this overlapping region.
Yeah.
Or NN4 will also do something. Right?
Yeah, that's right.
So when you actually compose the solution.
Yep.
How do you use simple averaging or
yeah, so it's a summation. This summation over J sums all the neural networks that are overlapping together. So for example, in this region here, you've got 4 overlapping networks. Yeah. So that summation will sum over 4. You have 4 of those networks, and that summation will have non-zero values. Their window function will be non-zero.
How do you solve for the overlap in calculating the overall solution? Especially when you're calculating the loss, are they all summed together, or do you like?
Yeah, okay, so this is a good question. So I'll go to the next slide. I think this will help. So let me just explain it in 1D, because I think it's easier to look at, and then I'll answer your question. So we're modeling the solution to this du by dt is cosine omega t. And first of all, this plot here is showing the subdomains in 1D. They're just overlapping subdomains in 1D. So we have 5 of them. You can see the overlapping regions here. And then the top here is the window function for each subdomain. So you can see the purple subdomain here has a window of 1 and then goes down to 0 outside of its subdomain. Can you see that?
Yeah.
And if I show you just the outputs of each individual subdomain network, that's what the top plot is showing there. And then in your head, if you can imagine summing all of those functions together, you would end up with the full solution. So so to get the full solution, we just sum these individual networks together. That's what we're doing with the summation.
It's kind of like a wavelet.
It's kind of like a wavelet, yeah, or it's a localization of these. You can, so if we go back to Chris's lecture, we think of these as like basis functions, and this is like a localization of that basis. It's another way to think of it. Yeah. Very nonlinear basis functions, by the way. Any questions? It's kind of it's important to understand this because we'll be coding this later. Yeah. That was the question someone else asked. So we just hard code them. And typically we choose just a regular domain decomposition. But learning them is a very good idea. I would definitely, we haven't had the time, honestly, but there's other work that has done that for other problems. So, yeah. Yeah.
So we have capital J subdomains, right?
Yeah.
So my question is still continuing to me. So we have an overlapping region, right?
Yeah.
So you were simply summing.
Yeah.
So one subnetwork will do some solution.
Yeah.
The other subnetwork is also doing so.
Yep.
So
yeah, so have a look in this region here. This is an overlapping region. So you've got two networks here, the green and the orange, and they both have a value of about -0.5. So the final solution is just the sum of those values, which should be about -1. So that's what this green line is showing. It's just summing all those individual curves together. It's only in the overlapping regions where you have contributions from multiple models.
Yeah.
Because of the locality of the basis, basically, of the window.
So this approach work for unstructured domains.
Yeah, so you can define whatever domain decomposition you want,
Yeah.
whatever window function you want. It's very flexible. All we're really doing is adding some locality to alleviate spectral bias. That's the goal. Yeah. Okay.
The smaller the overlap, the sharper the gradient.
The sharper the difference, yeah, exactly. And that becomes a bit dangerous because if you have a very narrow overlap, you have to have at least a few co-location points in that region for the networks to be able to communicate with each other when they train. Yeah, so
If you have a big overlap, then it kind of smooths this overlap.
it can still work. It's just a bit more computationally expensive because you're covering the same point with many networks instead of a few. But this is interesting to,
Basically, the deep overlap.
yeah.
it's, two domains, long.
So the problem with this method, there's multiple problems, but one of them is we're adding more hyperparameters, a lot more. So we have to be careful with that. But it does help. So one thing I want to point out, we train FP pins, so this model, with exactly the same loss function as a standard pin. Now to see that, you can just think of this whole thing as a special architecture, like a custom neural network architecture. Imagine that this is like the hidden state of the network, and then the final operation is like a summation, and you get the output is just the single scalar output that we're predicting. Or you can imagine a neural network architecture that's got like multiple subnets and they're all summing together to a final value instead of just a normal fully connected network.
So it becomes more like a finite element map.
Right. Yeah. So this is very analogous. I mean, we got the inspiration from FEM basically, is we want to use lots of elements and we have a small little basis in each basically that we're going to learn. That's why we call, well, kind of why we call them finite bases. Yeah.
Outside of the X range, outside of the domain.
Yeah, so you can call this is just another parameterized function. So you can call it with whatever value you want. You'll probably get a weird answer because it's not trained. It's just like a pin. It's not trained on anywhere beyond its modeling domain. Yeah. Okay. Yeah.
Use smooth function for the manipulation.
Yeah.
Instead of
it's important to, that's a great question. So we have to use smooth window functions. A sharp like step function is dangerous because you're introducing discontinuities in your final function. You've got a bunch of discontinuity stuff happening here. This thing here is also going to have some discontinuity of some type. And a lot of PDEs need to have continuous solutions like smooth solutions. So, but on the flip side, if you know that there's a discontinuity in your solution, you could bake that in somehow. Perhaps. Yeah.
The comment to that, so you
Yeah.
can of course use this also for non-physics training.
Yeah.
It also helps with the spectral bias.
Yeah.
And then you can do discontinuous for
Yeah.
data tuning that works also very well.
Yeah, so it's just a general architecture of a network that uses localization to alleviate spectral bias. That's all we're doing really. So yeah.
So,
Yeah.
so you know, this overlapping is.
Yeah.
You are not doing redundant compute, right? Because you are anyway going to sample your collocation points in a random fashion.
Yeah, so you're getting into the details, but it's important to make this efficient. We make sure, especially, we have a code base that implements FP pins. You can look at it, it's in the GitHub, you can link. But in that code, we make sure we only pass the collocation points to the networks that have non-zero values in their windows. A better way of saying that is we only give each subdomain network points in its subdomain. We don't give it all the points in the entire domain. And that's really important for efficiency. But in the code that you're going to write today, you're going to do it in a less efficient way, just for ease of use. But that is an extension you could try in the code. Yeah. Okay. Yeah, so this is, I tried to be a like-for-like comparison of that same pin setup, but now with FP pins instead. So kind of the same number of collocation points, same physics losses, etc. And all we're doing now is this domain decomposition, and each subdomain has one hidden layer and 32 hidden units, and we've got 15 subdomains. And yeah, I mean, you can see it immediately, it trains much faster. And our hypothesis is that we're alleviating the spectral bias factor. So yeah, this is the convergence curve of the pin versus the FP pin. So there's two interesting things. The first is the pin is much more accurate. The final accuracy is much higher. The other interesting thing is the x-axis here is not the time step of the gradient descent or the iteration step. This is actually the flops that are spent training. So who knows what a flop is? Some people don't. So can someone just tell me?
Floating point operation.
Yeah, floating point operation. So it's literally the number of individual operations that you have to run to train the network, like multiplies and divides and add additions and stuff. So the FP pin actually takes way less flops to train. Can anyone tell me why? Why is it in a flop perspective faster? Less parameters, yeah. So the really cool thing is that we can use much smaller neural networks in each subdomain. Remember in the pin, I had to go up to like 66,000 parameters or something.
The complete graph is also smaller than.
Yeah, but here maybe each subdomain has like a couple of hundred. Times that by 15, that's maybe 1,000. I couldn't train a pin with 1,000 parameters on this previous problem. So yeah, fundamentally we just need less parameters in the network. It's a more efficient representation of the solution. That was kind of a neat thing that I didn't realize when we came up with it. Yeah, so if you compare, we had this problem before, like empirically, we had these extra factors apart from the fundamental Nyquist scaling. And so this is what we found with FP pins, is we're kind of alleviating spectral bias. I don't know if we've completely got rid of it, but let's just say that we've crossed out that factor for now. So that gets rid of that S factor. And the F factor is increasing the number of subdomains. That's what the increasing the number of parameters in the pin as you increase frequency. So we don't need to do that in the individual subdomains. We can keep the size of the subdomain network fixed. So that's kind of, it gets rid of that factor as well. So yeah, they train, and that's what I showed in that plot. They train more accurately and they train much faster than a standard pin. So yeah, that lets us do things like this, like do actual multi-scale simulations with FP pins. This is a wave equation simulation of 3 different earthquakes with different frequencies propagating through some Earth model, basically. And it's quite a high scale, multi-scale simulation. We've got lots of reflections, lots of compressions at different frequencies. And I've never tried it, but I would bet anything on that a standard pin would just not train on this at all. It would just never work. So we were pretty happy with this. Our code is super efficient, or as efficient as it can be. So we were running on 60 by 60 by 60 subdomains in each direction. So that's like 200,000 neural networks being trained in parallel.
What's the time difference in the single simulation?
Yeah, I'm literally getting onto that. So, yeah, but 200,000 networks in parallel, but each network is very small, so it actually doesn't take much time to train. And about 9 million parameters in total.
In terms of memory, of course, this is very demanding. Yeah?
Well, there's 9 million total parameters, which is actually not that bad in terms of memory. If you think of like a finite difference simulation, you're going to discretize this onto a grid, and you might have 100 by 100 grid. How many parameters has that got? That's got quite a lot. Maybe it's not a million, but if it was 1,000 by 1,000, it would be a million. So yeah, it's maybe an order of magnitude, maybe.
What I'm just thinking is kind of, the same problem as, let's say, with finite elements. Let's say you have a small characteristic scale in the problem, epsilon, then the number of subdomains will be 1 over epsilon to the power of b. More or less the same as the finite.
Yeah, exactly. So everyone's kind of drawing analogies with FEM, so this is a very good way to do that, and we're going to get even closer coming up. So keep that thought going. Yeah, so it looks good. It's definitely a massive step forwards in terms of pins, but the issue is, just as Chris pointed out, I've got it on the slide now. This took 2 hours to train on a GPU using the most efficient code I could write. Maxing out the GPU, and this ran on 5 minutes on a CPU with finite difference time stepping. So we just I think it was like maybe a A100. I think it was single GPU. Yeah, but this is CPU. This is not. So yeah, we're not there yet. We've taken a step from pins to FP pins, but it's not there. Yeah, so you can brute force this, just like we brute forced going from PyTorch to JAX. But it's not, I think what you really need is a change in the algorithm fundamentally. And
because you previous slide, you are not evaluating all this like 200,000 batch.
Yeah, we're doing a VMAP in JAX to evaluate all of them at the same time in parallel on a GPU. Yeah.
Parallelization is already taken care of.
It's taken care of. Yeah, we've done it. Yeah. So this is the issue, really. Like, it is true that we crossed out those factors, at least empirically, and got down to omega to the d. But the problem is the constant in front of the big O notation. This is the time, the overhead that it takes in gradient descent to run your model forwards and then run it backwards to get gradients, and do that 1,000,000 times or 10,000 times to do gradient descent. That's just a massive overhead that takes a long time to run. And so that's my argument of this workshop, is that we have to find a way to avoid gradient descent or make gradient descent converge much more rapidly than what we're currently able to achieve. Does that make sense? I think it's kind of obvious, but at least from the evidence that I've given. Okay, so we're going to try and get rid of gradient descent. And we're coming up to kind of the state-of-the-art models that we're now doing research on. And what the idea that we had was to use extreme learning machines. So can anyone raise your hand if you've heard of an ELM or a random feature model or something like this. Okay, so not too many. So it's an extreme learning machine. I don't know if it was proposed in 2006, but this is a very famous paper. And they came up with this kind of crazy, it sounds crazy to start with, but they said, well, instead of trying to train all the weights of the neural network, which is a very nonlinear, expensive task, why don't we just randomly initialize and just fix all of the weights of the network and keep them fixed and just train the weights of the last layer? It sounds like a crazy idea, but it's actually really interesting because if you're using a fully connected network like this, so on the left is a standard way of doing it. Green means trainable. On the right is where we fix the blue weights and we just train the green weights. For a fully connected network, we can actually write the output here. It's a single output of the fully connected network as a summation over all of the last hidden activations times by the last layer weights A. So the last hidden activations, each of the hidden nodes, we just represent that as some other nonlinear function of the input X or T up here with some randomly initialized but fixed weights. Can everyone see how that is defined and how that makes sense? Any questions? Yeah.
To me, it looks like a mesh-free spectral method, and we know that in spectral methods, they work well for smooth problems.
Yeah.
Because of non-smooth problems.
Yeah.
Can you lose in expressivity?
Yeah.
Compared to neural net.
Yeah, right. Okay. I'll get onto that later because I think that's important. But you're drawing a good analogy. What we can think of this as basically a linear combination of nonlinear basis functions. We can think this is basically having k basis functions defined by the hidden state of the network. And we're just going to linearly sum them and just learn the linear coefficients to train the network. So that's the model.
But this setup will work only for this kind of fully connected data set. What about convolutions?
Well, so this basis can be any function you want it to be. So you could run like a convolutional network, grab the output and sum over k networks to get your convolutional basis, if you like. So it can be any randomly initialized and fixed network. Yeah. Okay, so why are we doing this? Well, it's going to turn out that what we've done is we've actually made this network linear in terms of the weights that we want to train. And that's really key, like turning something from a nonlinear function into a linear function in the things that we want to train is very powerful. So it's very simple. We're going to take the FP pins that we just learned. Remember we had neural networks in each subdomain. And all we're going to do is we're going to swap out the fully trainable networks with ELMs. So that's literally what I just did there, is just change the network in each subdomain. And what I did in the top right here is I just explicitly wrote that equation for the ELM in the full FP pin equation. So remember this full equation sums all the subdomain networks together and applies the windows to the subdomains. And the U here is still the output of the FP pin, the guess of the solution.
And the fixed weights in each domain is initialized differently, or?
So yeah, you can choose how you want to initialize each of the weights of each of the subdomains. We just do it the same way. So random initialization, but you can choose. So yeah, you've got these theta jk's now. So j is the number of subdomains and k is the number of basis functions per subdomain. So it's now adds an extra symbol. But can you see how we've got this still a linear summation over the coefficients for each ELM? Okay, so let's think about our PINN loss function again. So we had this harmonic oscillator. This is the physics loss. I'm just ignoring the boundary loss just so that I can show it on the slide, but everything carries over for that loss function as well. But this is the physics loss. And all we're going to do is we're going to substitute in our equation for the ELM FP pin into this loss function. See how I just substituted in, very simple. Can anyone notice anything about this? Anything special about this that we can manipulate this? How we can manipulate? Yeah.
The order of the sums or something.
Say again.
Swap the order of the sums.
Swap the order of the sums, kind of, yeah. The key thing to notice is that you can shift all the summation symbols to the left-hand side. And not only that, but you can shift the coefficients A to the left-hand side as well, to the left of the differential operator. Because crucially, the operator is a linear operator. So basically everything is linear here, all the way down to the weights of the hidden layers of the last hidden layer of each subdomain network. So I can do this. I've just rewritten this and used the fact that the operator, which I'm now abbreviating to n, applied to just this part of the equation, moving A to the left-hand side and shifting the summations to the left. I hope that makes sense to everyone. It should be fairly obvious. Okay, that's pretty cool, because if you stare at that long enough, you realize this, that you can immediately write this as actually a matrix equation. You can convert this into a matrix equation. So maybe you can just stare at it long enough, but you can realize that this loss is still a single value. That's, you're summing over all these things and then squaring. That's a scalar value. And if you took this matrix here, which is just each of these elements indexed by j, k, and I, like this, and times it by your vector of weights of the last layer of each subdomain network. For generality, we subtract a vector here, but in this case, that vector is just 0. And you end up with this matrix equation, which is simply a least squares problem. You just want to invert this matrix or solve the least squares problem to get the optimal value of A that minimizes L. Can everyone see that, at least conceptually, even if you're not sure about the indices? Yeah.
This is like the same thing as you're doing like the hierarchy schemes or something.
Yeah.
You want the first solution. So
Yeah.
Just plug in with different bases.
Yeah, exactly that. So again, we're converging to FEM. I'm gonna lay that out explicitly in a bit. So it's interesting to think about the shapes of this matrix. So this matrix is actually n, where n is the number of collocation points. So it has n rows, and jk is the number of subdomains times by the number of basis functions as the number of columns of the matrix. And then A here is just jk. So j is the number of subdomains, k is the number of basis functions. So it's just the total number of learnable weights that we have to learn. And h is n. You just think about the matrix equation, it has to be so. Okay. So what we've done is we've rewritten the loss in terms of a least squares problem. And yeah.
Just note, for example, because in case people often use hard constraints.
Yeah.
But if you use hard constraints,
Yeah.
you reduce the nonlinearity.
If you do that, there are ways to write hard constraints which are still linear.
Is it possible to see the problem as a quadratic optimization problem?
Yeah. Yeah, so
Like,
immediately now, as soon as we did this step where we showed that the loss function is now the same as this least squares problem, we're done. Now all we can do is just use this off-the-shelf least squares solver, of which there are many in NumPy, SciPy, etc. And we just solve the system. We have to assemble these matrices, or we have to evaluate these things, these elements. We can do that in JAX. It's just our differential operator applied to our window functions and our basis functions. We can evaluate that. So we can assemble this matrix. We don't know what A is, but then we just do the least squares solver to get it. Yep.
This time sounds more like
yeah. 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 Okay, so I really want to get to the slide because everyone's figuring it out. Let me get to that. So just before that, this is a least squares problem. Like standard least squares theory, you can show that the analytical solution is given by this matrix equation, where you just have to invert this matrix or do a linear solve to get A star. So you can use any off-the-shelf solver. You can use a CG method or even a least squares solver. Bad. We'll get onto that. Yeah, and yeah, so this is the key insight really, is that by using a linear combination of nonlinear basis functions, we turned the PINN loss from a nonlinear loss into a quadratic function, which turns it into a least squares problem, which we can solve with linear solvers. We've completely removed the need to do a gradient descent, or more generally like a nonlinear optimization, basically. Can everyone make that jump conceptually? Yeah. Cool. So yeah, we did it basically. We implemented that for this 1D harmonic oscillator. Same setup as before, but we're now using ELMs, and we figured out how to construct that matrix and then give it to a least square solver. And yeah, we find exactly what we were hoping for, which is, as before, the PINN just doesn't work. The FP PINN is much faster and more accurate, but still relatively slow. And the solver gets actually a better accuracy, slightly better, and is like an order of magnitude faster in the solve time. And now we're starting to approach like a traditional method. So yeah, it's pretty cool to be able to train the PINN and do PINNs but fast. So just to convince you a bit further, obviously that was a 1D problem. We've been doing it on more complex problems. So this is the Laplace equation. So this is a 2D problem. And we were actually interested in the scaling behavior. So the Laplace equation has this force on the right-hand side, and we specifically chose it so that we can increase the frequency of the solution here. And we also made sure that the solution had multiple scales, so like multiple sine waves, basically. And the most complex one has like, I don't know, 7 different scales of frequencies, and it's a very high frequency solution. And so we used ELM FP PINNs to solve all of these different problems. And this most complex problem had 5,000 subdomains, so like pretty large. And I won't go into it, but we also use multi-level domain decompositions. So we actually stack multiple domain decompositions together, inspired by multi-level methods. It really helps, but I'm not going to get into it. Long story short, the blue points here, so this is the accuracy on the y-axis and the time it took to solve on the x-axis. The blue points is the FP PINN training everything. And the green points is exactly the same setup, but just fixing the random weights, the hidden weights, and just doing a linear solve instead. And it we get that order of magnitude speed up using the linear solver instead of doing gradient descent, basically. And what I found interesting is you just don't need to train the hidden weights. That's what it's telling me. We're getting the same accuracy by just optimizing less. So yeah, that kind of starts to answer that question, like, is it a good idea to use random basis? I don't know yet, but it does work for these examples when compared to like fully training everything.
What was the smallest frequency in your problem?
It's kind of hard to say. It's you can see the kind of number of cycles though. There's maybe 60 cycles or something. It's quite high. So yeah, was there another question? Yeah. Oh yeah, error bars. So we initialized with different random weights, and we averaged.
The best extreme learning network has a really wide error bar.
Yeah, it does. So this is an issue or a sensitivity of ELMs. You have to care a lot about how you initialize your basis functions. It makes sense. So in some cases, the basis just didn't work out for some reason. Yeah.
Weights are fixed, right? So why does it matter?
Because what we did is we did different seeds. So we randomly initialized the weights many times and then averaged the results, or we reported error bars basically.
Sure, but in the extreme learning machines,
Yeah.
you fix most of the weights,
Yeah.
and you train only the last layer.
Yeah. But it might just be that one of those initializations had a poor set of weights that gave bad basis functions for some reason. So there's definitely a sensitivity there. So other people have looked at the initialization strategies of ELMs, and it's very important. That's a whole topic. Yeah.
Wondering because if you look at the groups, you cannot use the weights.
Yeah.
Let's say you have a parametric problem and then you retrain on some parameter, get this kind of basis.
Yeah.
And then you can use it for model reduction.
Yeah.
And you do that.
Yeah, definitely. So I'm going to get onto that. So let's move on. So what I did here is, I'll come back. What I did here is take a single subdomain and I plotted the basis. So I randomly initialized the weights, didn't train them. And so this particular cyan subdomain here had, I don't know how many, is that 8 or something, basis functions? And what you see is that they all look kind of linear. And the reason is because we use tanh functions as the activation function. And for shallow networks, the outputs of those basis functions kind of look like tanh functions because of that activation. So that's kind of interesting because what that does, if you look at this M matrix, this is the matrix in the least squares problem that we're trying to invert. You can see that these basis functions here are contained in the columns of the matrix. And what I'm saying is each of these basis functions is like kind of collinear. They're very linearly dependent or look linearly the same. So if you've done any work on kind of matrix problems, you'll know that this makes the conditioning of the system really bad. Or basically means that the solver will have a hard time getting to the solution. It will need a lot of iterations if you're using a CG method, for example. And one way you can look at this is you can actually take this matrix and you can look at the eigenspectrum or SVD spectrum or something. And this will tell you about the conditioning of the system. And what you're looking for is like a small magnitude range of eigenvalues. But here we've got a condition number, which is 10 to the 18 or something. It's really, really poor. So yeah, going back to your point, like maybe this is not the right basis for this problem. So this is one of the challenges. And so the solver we used, you could see that it took like 5,000 steps to converge, which is quite slow for a least squares solver. Yeah, go on. Yeah, next slide. Yeah. Sorry, yeah, I'm going on for a long time. Yeah, let's do it now. Let's actually do it now. Yeah, because I've got a few slides. Yeah, please take a break. So maybe 4:15. Yeah. Okay, everyone, are we ready? Okay, so we've got 1 or 2 more slides and then we'll get to the practical. You're going to be implementing an ELM FBPIN yourself. Sounds pretty scary, but I've done a lot of the coding for you, so there's only a few key things to do. But let's just go back to what I was just mentioning. We have this big linear or least squares system that we want to solve, and this matrix is usually poorly conditioned. And the reason is that the basis functions are, at least in this example, very collinear or have linear dependence. That makes it hard to invert this matrix. So someone already mentioned, why don't we just change the basis? So, well, actually before that, one option, a very good option is to use preconditioning. I'm not going to talk about that at all, but I would refer you to 2 excellent pieces of work. So one from Alexander and others who did kind of SVD-based preconditioning. And we also did some stuff using QR methods. You can have a look at both those papers if you're interested. But what I'm going to show here is literally swapping out the basis to something that's not even a neural network anymore. So at this point, when there's no neural networks in the picture, and this was like a thought experiment that I did, what if we just used polynomial basis, like a much more standard basis that we know approximates functions with Taylor series? And it's not actually that surprising, but it's kind of a proof that this still works. Is we can still approximate, train the PINN. This is the solution of the ELM FBPIN, but now it's a polynomial basis. And lo and behold, the matrix is much better conditioned. So this seems like a better basis. So you can kind of raise the question, like, should we even be using neural networks? And where are we heading? So, yeah.
Do you still need window functions, or can you get rid of window functions as well?
I think you still need it because polynomials are not bounded.
But you could choose them.
Yeah, you could. Yeah,
So that's the-
yeah, you could. Yeah, so then you wouldn't need it. Yeah, everything stays linear, so it's still good. Okay, so we'll come back to that point I just made, but I just want to point out another problem, which is that this matrix is absolutely huge. This is the Laplace equation that or example that I showed you before. And I think I told you that this matrix, well, if we're solving the normal form of the least squares problem, there's a matrix called A, and this matrix is JK by JK size. So J is the number of subdomains, K is the number of basis functions per subdomain. And so I showed you that example had 5,000 subdomains and 6 basis functions per subdomain. So that's like 1 billion elements in that matrix. So you couldn't even store that on a normal computer. That's I don't know how many gigabytes that would be, but crazy. So I've got a question for you. Like, how did we manage to get this speed up, even if the matrix is like not computable? Say again. Matrix free. Iterative solve. Yeah. Yeah. Sparse. Yeah, that's the key. That's the key insight. So the solution here was to exploit sparsity. So if you actually go into these matrices, what you realize is that most of the elements are 0. Anyone know why?
Because the domain decomposition are not coupled.
Yeah, it's to do with the domain decomposition. Can anyone elaborate? Say again. Local connections. Yeah. Yeah. Go on. Windows. Yeah, exactly. So each column and each row is basically a different basis function. And so the sparsity pattern is just saying which basis functions talk to other basis functions. And remember, like in that 2D example, we had like 4 overlapping subdomains. So for one basis function, there's only ever 3 other ones that are going to talk to it. And so you get basically a blockwise sparsity pattern here. And so that reduces the size of the matrix from like JK squared to something that's of order JK, like it's linear in JK, which is computable. It's basically linear in the number of parameters. And so, yeah, you mentioned we can use sparse solvers. So we don't explicitly compute the whole matrix. You will be computing the whole matrix in the example just for ease. But in our actual implementation, we just we define the matrix vector product and we just keep the non-zero values. And SciPy has a bunch of useful sparse lineage stuff that we just use. It's very easy.
But this doesn't run on the GPUs, right?
It does, so we haven't written on the GPUs for now. So actually those results, they were all on the CPU, which is kind of, we could get bigger speed up still. Yeah. Okay, I'm going to skip this. I'm just going to go straight to this original question we asked at the very start of the talk. And yeah, the kind of current state of the art was that PINNs are not competitive, and I would generally agree for forward simulation problems. But what we're showing is that if we think really carefully about the architecture, spectral bias, and replacing gradient descent, I think we can start to approach these kind of finite difference methods. And actually, I think a better question now is to ask this question, which is rather than can PINNs beat FEM, are PINNs becoming FEM? And I think there's been 4 or 5 people that have kind of pointed towards this already. And I would totally agree. Yes, that's definitely the case, at least from the direction that our research is going. So let me just frame that mathematically as concisely as I can. So this is fairly high level, but you should get the point. So yeah, let's just recap ELM FP PINNs. We have our differential equation. We have this FP PINN architecture that approximates the solution here. And we said that it's for an ELM FP PINN, it's a summation over these basis functions for each subdomain. And then we use our residual loss function. I've just shown the physics loss here. And we end up with a least squares problem. And I told you that this matrix is JK by JK, and it's sparse and symmetric. I showed you that it's sparse as well. And the problem boils down to just inverting this matrix or solving the problem. Okay, so let's look at the FEM. And this is not rigorous, but it's high-level description of FEM is good enough. And again, you start with your underlying equation. FEM then makes loads of finite elements locally defined, just like we locally define our with our window functions in the FEPIN. And in FEM, the task is to get the coefficients of those basis functions. So you can choose whatever basis you want, polynomial or otherwise, tenth functions, whatever. Typically, so this is one difference now, is we're using a nonlinear basis, like an extreme learning machine, rather than maybe a simpler basis. The other big difference with FEM is that with FEM, we use the weak formulation. So we take our EE residual, but then we times it by these test functions. We can often use the same basis for our test functions as our trial. But at the end of the day, if you're not familiar with FEM, it's okay. Basically, with a finite number of basis functions, this again boils down into a big matrix equation, where we have like stiffness equation matrices and things like this. And we need to invert this matrix or solve it to get A here. What's really interesting is if you look at the shapes of these matrices here in FEM, J by J often depends, but where J is the number of elements, and B here is J. And again, these matrices are sparse and symmetric, and we use that sparsity to create efficient FEM solvers. So also, when you use higher order FEM, you'll have like a K term here as well. So you'll have however many basis functions per element. So hopefully you can just see that boiling it down to the same computational problem is exactly the same. We're doing a matrix inversion or a similar shape matrix with the same kind of sparsity and symmetric nature. So yeah, I would definitely say from a mathematical point of view or a linear algebra point of view that we've just kind of converged to an FEM type solve. So yeah, I think that's it could be pessimistic that we're just going full circle, but I prefer to think of it as we're bridging these two fields now, where like the last 5-10 years, we've really thought of PINNs as its own bubble or community. And I think it's a much better thing to kind of bridge to traditional numerical methods. And as we've done that full circle, now we can like bring in ideas from both fields and see analogies in different ways. So I've had a lot of discussions with people already, like for example, adaptive remeshing in FEM. You could think of that as adaptive co-location points in PINNs, or maybe someone was talking about learning the domain decomposition. That's kind of like an adaptive remeshing.
Excellent line. So,
Or at least conceptually, right? Yeah.
sorry.
I understand, but all these kind of ideas, if you want to solve a nonlinear PDE, you can do the same tricks that we do with FEM for the FP-PIN ELN. So I hope that kind of is the punchline. And so the task now is for you to do the final practical. So you have just basically an hour, and you're going to take that FP-PIN, the PIN code, and the first step is to turn it into an FP-PIN and train it. And then the final step, if you get there, is to get rid of gradient descent and just train the last weights of the networks. So yeah, please get started, and I'll help you out. Yeah.